Tonight, we're going to explore one of the most basic parts of reality: gravity. You feel it every moment of your life. It keeps your feet on the ground. It holds Earth's atmosphere in place. It keeps Earth moving around the sun, and it controls the motion of galaxies billions of light years away. But here's the part that changes everything. Gravity is not actually a force, at least not in the way most of us were taught. It's something far stranger and far more beautiful. Think about what you believe gravity is. You drop an object, it falls. Simple. Since childhood, we're told that Earth's gravity pulls things downward, that gravity is a force dragging objects toward the ground, that the sun's gravity pulls Earth into its orbit. Most people believe this. Schools teach it this way, and it's not exactly wrong, but it's incomplete. It's like saying the Earth is flat because it looks flat when you're standing on it. That idea works for everyday life, but it misses what's really going on. Back in 1687, Isaac Newton published a book called Mathematical Principles of Natural Philosophy, usually known as the Principia. It's one of the most important scientific works ever written. Before Newton, ideas about why objects fell or why planets moved were mostly guesses, philosophical ideas. No clear rules. Newton changed that. He showed that the same thing that makes an apple fall from a tree also keeps the moon orbiting Earth and Earth orbiting the sun. That was revolutionary. Before this, people believed the heavens followed different rules than life on Earth. Newton showed they were governed by the same laws. His law of universal gravitation says that every object in the universe attracts every other object. The stronger the masses, the stronger the attraction. The farther apart they are, the weaker it becomes. That sounds complicated, so let's slow it down and break it apart. Long before the concept of gravity was formalized, early civilizations looked up at the sky and saw a universe governed by rules beyond their understanding. To these ancient people, the night sky was a vast, mysterious canvas where celestial bodies danced with purpose and meaning. The stars, planets, and moon were not just distant objects but vital parts of stories, myths, and religious beliefs shaping their worldview. Many cultures observed that objects fall straight down and that the moon moved predictably across the sky. Yet, they did not interpret this as a universal force pulling everything toward a single point. Instead, their understanding was rooted in myth, spirituality, and tradition. The Babylonians, for instance, charted the sky meticulously, tracking planets and stars over generations. They viewed celestial phenomena as signs from the gods, powerful and unpredictable. When an object fell, it was not seen as an invisible force acting on it, but as something obeying divine will or fate. The sky was governed by gods, who controlled the natural order, and celestial motions were expressions of divine patterns. Similarly, the ancient Egyptians saw the universe as reflecting divine order, with their gods overseeing cosmic activity. Their understanding of weight and falling objects was intertwined with spiritual beliefs. They perceived natural cycles and phenomena as reflections of heaven's will. The idea that objects fell because of an intrinsic force was absent. They believed divine authority directed natural efforts and laws. In Greece, during the classical period, ideas began to shift, though still rooted in myth. Philosophers like Aristotle proposed that heavier objects fall faster than lighter ones, a notion that persisted for centuries. Aristotle didn't think in terms of universal laws, but saw motion as driven toward a natural resting place, on Earth or celestial spheres. Gravity was not a force pulling objects downward, but a natural tendency for earthly things to seek their proper place. The idea of a force acting on objects was linked to teleology. Things happened because they were meant to happen. During the Hellenistic period, these ideas started to change more substantially. Aristarchus and Eratosthenes made measurements of celestial bodies, moving toward a more empirical understanding. Yet even these efforts were filtered through mythic and philosophical frameworks, and the notion of a universal force like gravity was not yet conceived. Explanations relied heavily on geometric models and divine intervention. To the east, Indian philosophers and astronomers also explored celestial motion. They viewed the universe as cyclical, driven by divine or abstract principles, sometimes mentioning attraction or pulling, but usually intertwined with spiritual ideas, not physical laws. Their texts sometimes referred to forces of attraction, but these were more spiritual than scientific. In China, early cosmological theories focused on balance, harmony, and the influence of celestial spirits. Movement of celestial bodies was seen as part of a connected system governed by cosmic energies and moral order. Gravity, as understood today, did not exist in their worldview. The universe reflected harmony among vital energies. Early civilizations understood gravity or falling objects through divine will, myth, and harmony, rather than universal forces. The notion of a single, invisible force pulling objects toward a center was absent. Instead, explanations connected to the intrinsic nature of objects, divine decree, or cosmic harmony. Few cultures attempted consistent physical explanations for falling objects, and those that did, like Aristotle, relied on ideas now considered outdated, such as the belief that heavier objects fall faster because they have more natural weight and strive toward their natural place. These were intuitive explanations based on everyday experience, but lacked scientific understanding of forces acting at a distance. It wasn't until the scientific revolution that the concept of a universal force, capable of acting across a vacuum without contact, gained prominence. Newton's law of universal gravitation revolutionized humanity's understanding, transforming mystical notions into a mathematical framework. Newton's idea was a blend, a scientific advance rooted partly in philosophical and religious ideas, yet paving the way for modern physics. Despite this advancement, early civilizations did not perceive gravity as a measurable or predictable force. Instead, they believed the universe was governed by divine or spiritual principles. Natural phenomena were signs or manifestations of a larger order, often mystical. The idea that objects fall because of an inherent universal force was outside their conceptual scope, awaiting future scientific discovery through observation, experimentation, and mathematics. Understanding how ancient cultures viewed gravity sheds light on human curiosity and the evolution of thought. From divine command to natural law, early perceptions laid the groundwork for modern physics, even if rooted in myth and belief. Their perceptions of the universe's mysteries still echo today, reminding us that what seems obvious now was once wonder, speculation, and faith. Understanding gravity has been one of the most fascinating and perplexing quests in human history. Over thousands of years, our grasp of this invisible force has evolved, shaped by daring thinkers, groundbreaking experiments, and revolutionary theories. Let's walk through some of the most pivotal milestones that have defined our journey toward understanding gravity. It all begins in ancient times, where early civilizations looked up at the sky and sought explanations for the celestial dance of planets, stars, and moons. The Babylonians observed planetary motions with remarkable accuracy, but attributed their movements to divine will or mystical forces. The Greeks too mused about celestial phenomena, with Aristotle proposing that objects fall at speeds proportional to their weight, believing that heavier objects fall faster than lighter ones, a notion that would persist for centuries despite its inconsistencies. Then came the groundbreaking figures of the medieval and early Renaissance periods. Perhaps most influential among them was Nicholas Copernicus in the 16th century. He challenged the geocentric view that placed Earth at the universe's centre, proposing that the Sun, not Earth, was at the centre, his heliocentric model. While this was revolutionary in understanding our place in the cosmos, it didn't directly address gravity. Instead, it set the stage for further exploration of celestial mechanics. The first truly scientific breakthroughs related to gravity stem from the work of Galileo Galilei in the late 16th and early 17th centuries. Galileo's experiments with inclined planes and his famous observation that objects of different masses fall at the same rate, contrary to Aristotle's theory, laid the groundwork for questioning existing assumptions. His findings suggested that acceleration due to gravity was constant regardless of an object's mass, challenging centuries of accepted wisdom and opening the door for a more precise scientific approach. The next major milestone arrived with Sir Isaac Newton. In 1687, Newton published the Principia Mathematica, a tome that would change the entire concept of gravity forever. He described gravity as a universal force. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This was a seismic shift. Not only did Newton mathematically define gravity, but he also unified terrestrial and celestial mechanics under one elegant law. Falling apples, orbiting planets, and the tides all fell under Newton's comprehensive framework, giving humanity its first predictive grasp of how gravity worked. Newton's laws reigned supreme for the next couple of centuries, but they also revealed limitations. As scientists pushed further into understanding the cosmos, especially at very high speeds and in strong gravitational fields, the Newtonian picture began to strain under new evidence. It was clear that a more complete understanding was needed. Enter Albert Einstein in the early 20th century. His special theory of relativity, published in 1905, challenged Newtonian notions of absolute space and time, but it was his general theory of relativity, introduced in 1915, that would revolutionize our understanding of gravity itself. Einstein proposed that gravity was not a force acting at a distance, but rather a curvature of space-time caused by mass and energy. Imagine placing a heavy ball on a stretched rubber sheet. The ball creates a dent, and smaller objects nearby roll toward it. This became a vivid analogy for how mass tells space-time how to curve, and curved space-time tells mass how to move. One of the first major confirmations of Einstein's theory came in 1919, when astronomers observed the bending of light from distant stars around the Sun during a solar eclipse. This bending matched Einstein's predictions with astonishing accuracy, catapulting him into global fame and firmly establishing general relativity as the new paradigm for gravity. Following Einstein's revelations, the understanding of gravity entered a phase of intense exploration and technological advancement. Scientists began to test the extremes of Einstein's equations. During the 20th century, phenomena such as black holes, regions of space where gravity is so intense that not even light can escape, became theoretical realities, further underscoring how much our comprehension of gravity had deepened. In the latter half of the 20th century, we saw the launch of space-based experiments and observatories designed to test the predictions of general relativity in the most extreme environments. The Gravity Probe B mission, launched in 2004, measured how Earth's mass warps space-time, confirming the frame-dragging effect predicted by Einstein. Also, gravitational wave detectors like LIGO, operational since 2015, have detected ripples in space-time caused by colliding black holes and neutron stars, waves that Einstein's equations predicted a century earlier, but had never been directly observed until this century. These gravitational waves opened a new window into the universe, allowing scientists to observe phenomena that would otherwise remain hidden. They confirmed key aspects of Einstein's theory and gave us insights into the most violent cosmic events. In essence, we've moved from a universe where gravity was a mystical, mysterious force to one where its effects can be mathematically modelled, visually mapped, and even directly measured. In recent decades, efforts have turned toward understanding gravity's role in the larger universe, especially in the context of dark matter and dark energy. The observed acceleration of the universe's expansion and the motions of galaxies suggest that a large portion of the universe's mass-energy content is due to unseen components that interact gravitationally. These phenomena continue to puzzle scientists and challenge our current models, pushing us toward theories that might unify gravity with quantum mechanics, an elusive goal that might one day unlock the true nature of gravity at the smallest scales. Throughout this history, a recurring pattern emerges. Each answer leads to new questions, and each new discovery uncovers deeper mysteries. From the ancient Greeks' intuitive notions to Einstein's geometric view of space-time, our understanding of gravity has continually evolved. Still, the complete picture remains elusive. Could gravity be a manifestation of a deeper, more fundamental force? Might it be the key to unifying all forces in nature? These are questions that keep physicists awake at night, staring into the fabric of space-time, searching for the next milestone. As we chart our journey through the milestones in understanding gravity, it becomes clear that the story is far from over. Every planet orbiting a star, every ripple on the fabric of space-time confirmed by modern detectors, reminds us that gravity is as mysterious as it is fundamental. It can hold galaxies together, shape the universe's evolution, and perhaps, in the end, reveal the ultimate secrets of existence itself. Newton's formulation of the law of universal gravitation was not an instant discovery, but the result of years of observation, thought, and synthesis. He drew from earlier thinkers and added his insights. To understand how Newton arrived at his law, we need to explore the ideas and discoveries that shaped his thinking. In the late 17th century, the universe was largely mysterious. The dominant view was Aristotelian, which separated celestial and terrestrial realms. However, astronomers like Johannes Kepler challenged this idea through careful observation. Kepler analysed data from Tycho Brahe and formulated 3 precise laws describing planetary motion. These laws weren't mere qualitative statements. They were mathematical descriptions that accurately matched observations over decades. Kepler's first law stated that planets move in ellipses with the Sun at one focus. The second law revealed that a line from a planet to the Sun sweeps out equal areas in equal times, indicating variable orbital speeds. The third law related orbital periods to the size of the orbits, asserting that the square of a planet's period was proportional to the cube of its semi-major axis. These laws described what planets did but didn't explain why they moved this way. Kepler believed a force influenced planetary motion, but lacked a physical explanation. He understood that a force might act at a distance, but he lacked a framework for this idea. The concept of gravity as an invisible force operating across space was not yet established. Newton inherited this puzzle. When he set out to understand planetary motion, he didn't accept Kepler's laws as mere empirical facts. Instead, he sought a universal principle explaining all motion, both terrestrial and celestial. His goal was to unify the physics of heavens and earth under one law. Newton's breakthrough came from several key insights. First, he was influenced by Galileo's idea of inertia, that objects tend to remain in their current state of motion unless acted upon. Galileo showed that falling objects accelerate uniformly, indicating a link between gravity and acceleration. This suggested to Newton that the same force responsible for objects falling on Earth might also govern celestial motion. Furthermore, Newton wondered, if apples fall from trees because of gravity, why wouldn't the moon fall onto the Earth? The same force might be acting on both, just on different scales. This was a revolutionary idea, a universal force affecting all matter, terrestrial and celestial. Others had suspected gravity could act at a distance. Robert Hooke, for example, proposed that gravity might diminish with the square of distance, but Newton was the first to incorporate these ideas into a rigorous mathematical framework. He hypothesized that the force depended on the masses involved and the distance separating them. If true, this could explain planetary motions as consequences of such a force. To develop a precise mathematical form, Newton employed calculus, a new mathematical tool he helped develop. Calculus allowed him to describe changing quantities, such as a planet's velocity under a force. Using calculus, Newton deduced that the force between two objects was proportional to their masses and inversely proportional to the square of the distance between them. This formulation expressed as A Fs GSS GR frees M1 M2, 2, where GSS is the force, hvor M1 nend, and hvor M2 sim are the masses, hvor R is the distance, and Orn is the gravitational constant. Newton could not initially measure their Gaussian directly, but could determine it through observations. This mathematical law could reproduce Kepler's empirical laws if applied correctly. The inverse square law of gravity explained planetary elliptical orbits with the Sun at focus, consistent with observations. It also explained phenomena like cometary orbits and objects falling to Earth, unifying celestial and terrestrial physics under a single, mechanistic principle. Newton was driven by the desire for universality. He believed the same force governed all objects regardless of size or location. This was groundbreaking in an era where the heavens and Earth were studied separately. His synthesis was revolutionary, tying together observations and hypotheses into one coherent model. He also relied on the work of others. He acknowledged Kepler's laws, Galileo's findings on acceleration, and Hooke's ideas about inverse square relationships. Newton's genius was in synthesizing these clues into a single, elegant mathematical law. The key realization was that an inverse square dependence could produce Kepler's elliptical orbits. Using calculus, Newton demonstrated that if a force acts with this law, the resulting planetary motion would naturally be an ellipse, with the Sun at one focus. This bridged the divide between celestial and terrestrial physics, grounding all motion in a universal force. Newton's law transformed the problem of planetary motion into a solvable mathematical question. It enabled predictions of planetary positions, comet paths, and tides, all rooted in gravitational principles. His formulation wasn't just a new law, it was a powerful unification of physical phenomena. The significance of Newton's law lies in its broad explanatory power. It shifted science from qualitative descriptions toward precise mathematical laws and opened the door for ongoing scientific development. It demonstrated that the universe could be understood through observation, critical thinking, and mathematics. At its core, Newton's formulation reflected a profound conceptual breakthrough. He believed that everything in motion, whether apples falling or planets orbiting, was governed by the same force, following the same law. This unification changed physics forever, marking the start of modern scientific understanding. Newton's law served as a bridge between empirical observations and theoretical understanding. It turned a complex puzzle into a framework for prediction and analysis. The law's elegance and power exemplified a new era of scientific reasoning, a shift toward a universe explained by universal principles, expressed through mathematics. Finally, Newton's work showed that the universe operated under a single unifying force, accessible through careful observation and mathematical formulation. This insight laid the groundwork for centuries of progress, swinging science into a new realm of rational inquiry. His formulation of gravitational law was more than a set of equations. It was a paradigm shift. It proved that nature's underlying principles could be discovered through systematic analysis and reasoned synthesis, inspiring future generations to seek the fundamental laws of the universe. Classical theories of gravity, primarily rooted in Newtonian physics, once seemed to offer an elegant and comprehensive understanding of one of the universe's most fundamental forces. Sir Isaac Newton's law of universal gravitation painted a picture of a force acting at a distance, binding the cosmos together with a simple inverse square law. It described how every mass attracts every other mass in the universe, and this attraction diminishes as the square of the distance increases. It was a groundbreaking insight that explained the orbits of planets, the fall of apples, tides, and countless other phenomena with remarkable accuracy for its time. Yet, despite its genius simplicity, Newtonian gravity was not without profound limitations. For one, it relied heavily on the notion of action at a distance. Newton himself was troubled by the idea that objects could influence each other instantly across vast emptiness without any physical medium or intermediary. The concept of an invisible force pulling on objects without any apparent mechanism felt somewhat unsatisfactory. It left open the question, how was this instantaneous interaction possible? There was no explanation within Newton's framework for how the force propagated, or how changes in one part of the universe could instantaneously be felt elsewhere. Furthermore, Newton's theory faced challenges when it came to describing the behavior of gravity in extreme conditions. For instance, it could accurately predict the movement of planets in our solar system most of the time. However, subtle deviations, such as the precession of Mercury's orbit, hinted that the Newtonian picture wasn't complete. While these anomalies could be accounted for through complex calculations, their existence signaled that Newton's formula might be an approximation rather than a final answer. The advent of Einstein's special relativity presented an even more significant limitation. Newton's gravity did not incorporate the concept that nothing can travel faster than the speed of light. Yet, in Newtonian physics, gravitational effects were instantaneous. Changes in mass distribution would be felt instantly across the universe. This violated the relativistic principle that information, or any influence, cannot travel faster than light. This raised a fundamental conflict with our modern understanding of causality and the fabric of space-time. Additionally, Newtonian physics struggled to explain phenomena involving massive, dense objects like black holes or neutron stars. The equations predicted singularities, points of infinite density and zero volume, where the laws of physics as known break down. These mathematical infinities signaled a breakdown in the theory's predictive power under extreme conditions. They indicated that a more comprehensive framework was needed to understand what happens when gravity becomes extraordinarily intense. Another limitation was that Newton's law did not integrate with the other fundamental forces, electromagnetism, the weak and the strong nuclear forces. These four forces of nature are described by quantum mechanics, yet gravity remained stubbornly outside this quantum realm. It was an outlier, a classical force that refused to fit into the quantum picture, hinting at a deeper, more unified theory that could reconcile the microscopic with the macroscopic. Perhaps most compellingly, Newton's gravity lacked the ability to explain the universe's large-scale structure and evolution. It was primarily a force description suitable for familiar everyday phenomena and celestial mechanics, but it said little about the origin of the universe or its ultimate fate. it also could not account for dark matter or dark energy, components of the universe that seem to influence gravitational behavior on cosmological scales, but remain elusive in terms of direct detection or explanation within classical frameworks. The simplicity of Newtonian gravity, while its strength in many contexts turned out to be a double-edged sword, its inability to handle high velocities, extreme densities, quantum effects, or the dynamic structure of space-time illuminated its fundamental rifts with the actual workings of the universe. It became clear that a new theory was necessary, one that could uphold causality, incorporate the finite speed of information, and unify gravity with the other forces. Einstein's general theory of relativity addressed many of these limitations but introduced its own complexities. Instead of a force acting at a distance, gravity in relativity is depicted as the curvature of space-time caused by mass and energy. This geometric interpretation eliminated the problematic notion of action at a distance and resolved inconsistencies with relativity. It explained why gravitational influences propagate at the speed of light, and it provided the tools to understand phenomena like gravitational waves, black holes, and the universe's expansion. Yet, even Einstein's theory isn't the final word. While it has passed every experimental test so far, it still grapples with the quantum realm, where microscopic particles dance to different rules. The quest for a quantum theory of gravity continues, aiming to reconcile the classical and quantum pictures into a unified understanding of the universe. In the grand narrative of scientific progress, classical theories of gravity served as critical stepping stones. They were remarkably successful in explaining a vast swathe of phenomena, yet their limitations revealed the universe was more intricate. They couldn't explain the propagation of gravitational influence at finite speeds, the behavior under extreme conditions, or their incompatibility with quantum physics. These shortcomings sparked decades of research, ultimately transforming our picture of the universe, shifting from Newton's elegant equations to Einstein's geometric space-time, and now, in the modern quest for quantum gravity, to new frontiers still waiting to be explored. The limitations of classical gravity remind us that models are nature's approximations, stepping stones toward deeper, more complete truths. As profound as Newton's law is in its simplicity, it is just the beginning of understanding the vast mysterious force that shapes our universe, one that we are still, in many ways, only beginning to comprehend. Einstein didn't just tweak the existing ideas about gravity. He tore apart the old framework and built something entirely new, something that shifted our entire perception of the universe. To truly understand how revolutionary this was, we need to step back a bit and see what was believed about gravity before Einstein stepped into the picture. For centuries, Newton's law of universal gravitation was the gold standard. Isaac Newton described gravity as a force, an invisible, action-at-a-distance force that pulls apples from trees and planets around the sun. According to Newton, every mass exerts a gravitational pull on every other mass in the universe, and this force diminishes with the square of the distance between them. It's intuitive, straightforward, and mathematically elegant, but it also left critical questions unanswered. How does this force actually propagate? Is there a medium through which gravity acts? Newton himself struggled with these questions, but his law remained remarkably effective at predicting planetary motions and celestial mechanics. And yet, beneath that success lay a hint of something incomplete. Newton's theory didn't specify how changes in gravitational influence propagate. If the sun were to suddenly vanish, how quickly would Earth notice? The answer, according to Newtonian physics, would be instantaneously, an idea that doesn't sit well with the emerging understanding of how the universe works, especially regarding the finite speed at which information can travel. Fast forward to the dawn of the 20th century. Scientists and mathematicians were starting to realize that the universe was far stranger and more complex than Newton's elegant equations could explain. Einstein's journey into the depths of physics was motivated by the idea that gravity might be more than just a force. Perhaps it was something intimately tied to the fabric of space-time itself. In 1905, Einstein published his special theory of relativity, which put strict limits on the speed at which information could travel. Nothing could move faster than light. This was a seismic shift. It suggested that the concept of instantaneous action at a distance was incompatible with the rules of relativity. How could gravity operate if it needed a medium or instant communication? This question haunted physicists for years. Then in 1915, Einstein completed his general theory of relativity. Now he was doing something truly radical. He proposed that what we feel as gravity wasn't a force pulling objects together, but a consequence of the curvature of space-time caused by mass and energy. Massive objects like the sun or a black hole deform the fabric of space-time around them, shaping a sort of four-dimensional landscape in which everything moves. Just as a rolling ball on a curved trampoline will naturally roll toward the lowest point, planets and stars follow the curvature of space-time. What appears to be a force, gravitational attraction, is actually the result of objects following the natural straight-line paths, or geodesics, in this curved space-time. This idea was revolutionary because it changed the question from what force pulls the planets to how does the presence of mass and energy warp space-time. It also answered Newton's question about the propagation of gravity. Changes in the curvature of space-time propagate at the speed of light, not instantaneously. When the sun moves slightly, the distortion in space-time changes, and that change takes time to reach Earth, just as Einstein's equations predict. One of the landmark predictions of Einstein's theory was the existence of gravitational waves, ripples in the fabric of space-time caused by massive accelerating objects like colliding black holes or neutron stars. These ripples travel outward at the speed of light, transferring energy through the universe in a way that Newtonian physics couldn't accommodate. The detection of gravitational waves in 2016 by LIGO, Laser Interferometer Gravitational Wave Observatory, confirmed this aspect of Einstein's vision, a world where gravity is like a dance of space-time fabric, oscillating and rippling. Einstein's equations also introduced the concept of the cosmological constant, a term he added to account for a static universe, something later discarded when the universe was found to be expanding, but reinstated as a measure of the energy density of space itself, that dark energy. This insight showed that the fabric of space-time isn't static. It evolves, expands, contracts, and interacts in ways Newton never envisioned. The impact of Einstein's revolution extended beyond pure physics. It reshaped our understanding of reality itself. No longer was gravity a mysterious force acting over distance, but a manifestation of geometry. This geometric view elegantly explained phenomena that Newton's laws couldn't, such as the precise orbit of Mercury, whose perihelion precession couldn't be fully accounted for before Einstein. The theory also predicted the existence of black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These aren't just theoretical oddities. Astronomical observations over subsequent decades have found compelling evidence of black holes lurking in the centers of galaxies and throughout the universe. The understanding that gravity can so drastically distort space-time was an idea Einstein gifted us that continues to shape our cosmos. Furthermore, Einstein's general relativity challenged the very fabric of how we viewed space and time as separate entities. Instead, he proposed that they are part of a unified fabric, space-time, that can bend, stretch, and ripple. This concept gave birth to whole new areas of science, from cosmology to quantum gravity, and continues to inspire groundbreaking research. So how did Einstein truly revolutionize our understanding of gravity? By shifting the paradigm from a force acting at a distance to a geometric property of spacetime itself. He showed us that mass and energy tell spacetime how to curve, and that curvature directs the motion of objects. This elegant marriage of geometry and physics not only explained existing anomalies, but predicted phenomena that have only recently been observed, confirming the profound depth of Einstein's insight. Imagine a universe where gravity is no longer a mysterious force, but a malleable, dynamic feature of the universe's very structure. Einstein opened the door to that universe, a universe where gravity is woven into the fabric of space-time, changing the way we see everything from the motion of planets to the fate of galaxies and the evolution of the entire cosmos. It was a leap into a more profound, more accurate picture of reality, and that leap is still reshaping science today. The question of how we can be certain that gravity is a real, measurable force, rather than just a cosmic coincidence, has driven physicists to perform groundbreaking experiments over the centuries. These experiments prove that gravity isn't just a philosophical idea or poetic metaphor. It's a fundamental aspect of nature, observable, measurable, and predictable with astonishing accuracy. One of the earliest experiments that confirmed gravity's existence was Sir Isaac Newton's observations of falling objects and planetary motions. Although Newton didn't perform a specific experiment, his formulation of universal gravitation was based on careful observations of celestial bodies like Jupiter's moons and planets. The famous story of the apple falling from a tree symbolizes the primitive principle, how gravity pulls objects toward Earth. Newton's theories explained celestial motions and introduced the idea that objects attract each other with a force proportional to their masses and inversely proportional to the square of the distance. Centuries later, experiments in lab settings explicitly confirmed gravity's nature. One landmark was weighing the Earth itself, indirectly proving gravity's pull. In the late 1700s, Dutch physicist Christian Huygens performed torsion balance experiments, measuring tiny deviations in Earth's gravitational field, showing gravity's strength varies slightly with location and mass distribution. These experiments didn't measure gravity directly, but confirmed its influence on objects under different conditions, establishing gravity as a quantifiable force. Moving into the 1900s, the most direct proof came from tests like Michelson and Morley's interferometry, which aimed to detect Earth's motion relative to the luminiferous ether. Their precise measurements found no evidence of the ether, prompting a re-evaluation of physics and leading Einstein's theory of relativity. Einstein's predictions required experimental validation, which came through other experiments. In 1916, during a solar eclipse, astronomers observed the apparent positions of stars near the Sun and found their light bent in accordance with Einstein's predictions. This was a direct confirmation of gravity's effect on light, a radical idea at the time, and validated Einstein's general theory of relativity. It showed that gravity influences not just matter but also light, a groundbreaking insight. Laboratory experiments with torsion balances by Henry Cavendish in the late 1700s remain iconic. Cavendish used delicate lead spheres and a torsion balance to measure tiny deflections due to mutual gravitational attraction, ultimately allowing him to calculate Earth's density. His precise measurements demonstrated the tangible nature of gravity acting between known masses at small scales, confirming gravity as a force acting between objects we can handle and measure directly. Fast forwarding to the modern era, technological advances enable us to test gravity with highly sensitive instruments such as atom interferometers, quantum devices capable of detecting tiny differences in gravitational acceleration. These measurements confirm that gravity's effects are universal and consistent even at scales previously unreachable. One key modern experiment tests the equivalence principle, which states that gravitational and inertial masses are identical. In 1961, Laurent Eötvös used a torsion balance to compare the freefall acceleration of different materials, like lead and aluminum, uncovering no detectable difference within very strict limits. This supports Einstein's assertion that all objects fall at the same rate, regardless of their composition, reinforcing the universality of gravity. Lunar laser ranging is another profound test of gravity's consistency. Since the 1960s, reflectors left on the Moon by Apollo missions enable precise laser measurements of the Moon's orbit. These measurements confirm Einstein's predictions, showing the Moon and Earth obey gravitational laws remarkably well over millions of miles and billions of years. Such experiments reveal gravity's effect on astronomical scales, strengthening our confidence in its existence. Experiments at CERN using particle accelerators have explored gravity's quantum aspects, notably the search for gravitons, hypothetical quantum particles mediating gravity. While these particles have not yet been directly observed, ongoing research aims to detect quantum gravitational effects, seeking to confirm gravity as a fundamental force compatible with quantum physics. The detection of gravitational waves marks perhaps the most recent and striking confirmation. In 2016, LIGO announced its first observation of energy ripples in spacetime, caused by colliding black holes billions of light-years away. These waves subtly change spacetime distances, which LIGO's detectors measured with remarkable precision. Since then, multiple events have confirmed Einstein's prediction that accelerating masses produce gravitational waves, opening a new window for understanding the universe's most violent phenomena. Each experiment, Newton's celestial observations, Cavendish's torsion balance, Einstein's predictions confirmed by star-bending gravitational wave detection, contributes to a monumental chain of evidence. They demonstrate that gravity is a real, concrete force acting across scales, from terrestrial laboratory masses to cosmic events. We have measured gravity directly, observed its influence on light and matter, and captured waves rippling through space-time. Despite these confirmations, the true nature of gravity remains a profound mystery. Is it simply a force, or a manifestation of space-time curvature woven into the universe's fabric? The experiments have shown its effects, but have also raised questions that inspire further inquiry. Understanding what gravity fundamentally is continues to challenge scientists, pushing the boundaries of physics. As our measurements grow more precise, new questions arise. The quest to unify gravity with quantum mechanics, identify gravitons, and understand space-time itself continues to inspire scientists worldwide. The experiments confirm that gravity is a real, measurable force with undeniable effects, yet its true essence remains elusive. These investigations have built a solid foundation of evidence, but they also beckon us to look deeper into the universe's mysteries. In sum, from Newton's observations to the detection of gravitational waves, experiments have confirmed that gravity acts across all scales, shaping our cosmos. They establish gravity as a fundamental force, but ongoing research continues to probe its deepest nature, challenging and inspiring the scientific quest to understand the universe at its most fundamental level. Imagine the universe as an immense invisible pond, rippling outward whenever a stone is thrown into it. These ripples are not water waves but gravitational waves, distortions in the fabric of space-time itself. They travel through the cosmos at the speed of the light, carrying whispers of some of the universe's most cataclysmic events. But what makes gravitational waves such a groundbreaking piece of evidence for Einstein's general theory of relativity? Let's explore this fascinating story. To understand this, we need to consider Einstein's predictions from 1916. His equations of general relativity described gravity as the curvature of space-time caused by mass and energy, not as a force acting at a distance. Whenever massive objects accelerate, say two black holes spiraling toward each other, they should emit gravitational waves, ripples traveling through space-time. These waves are a natural consequence of Einstein's field equations but remained undetected for decades. Initially, the idea of gravitational waves was debated fiercely. Some skeptics doubted their existence because detecting such tiny ripples seemed impossible at the time. Einstein himself was cautious, but confident, realizing their existence was a logical outcome of his theory. The challenge was to confirm their existence experimentally. By the late 20th century, technological progress made this goal more feasible. Instruments called interferometers were designed to measure gravitational disturbances by sending laser beams down long arms, detecting infinitesimal shifts. LIGO, the Laser Interferometer Gravitational Wave Observatory, became the most sensitive detector of its kind. On September 14, 2015, LIGO detected gravitational waves from merging black holes about 1.3 billion light-years away. The signal was a faint but unmistakable chirp, increasing in frequency and amplitude, precisely as predicted by Einstein for black hole mergers. This was more than an intriguing observation. It was direct, compelling evidence that gravitational waves exist. How does this detection confirm Einstein's theory? The properties of the observed wave match detailed numerical simulations based on general relativity. Every phase, the inspiral, merger, and ringdown of the final black hole, aligned with Einstein's equations. This was a direct observation of space-time vibrations, not just effect-based inferences like the orbital decay of binary pulsars. Before this, evidence for gravitational fields obeying Einstein's predictions came from the Hulse-Taylor pulsar, a binary neutron star system with orbital decay matching gravitational wave emission predictions. However, that was indirect, observing the effects rather than the waves themselves. LIGO's detection was a landmark because it directly captured gravitational waves, confirming their reality and behavior as Einstein predicted. This discovery also validated the mathematical framework of general relativity and strong field regimes. Alternative theories of gravity predicted different wave behaviors. The exact match of observed signals with Einstein's predictions meant his model remains robust even under extreme conditions such as colliding black holes at significant fractions of light speed. Furthermore, gravitational waves have expanded cosmic observation tools. Before their detection, astronomers relied solely on light, visible, X-ray radio, emitted by cosmic events. Gravitational waves provide a new view, not absorbed or scattered by matter. revealing phenomena hidden behind dust clouds or in opaque regions. They offer insights into energetic and enigmatic processes otherwise inaccessible. The fact that Einstein's equations predicted these ripples and that they have been observed is a powerful endorsement of his revolutionary view of gravity. It confirms gravity propagates through space-time at the speed of light, propagating whenever catastrophic events occur. This confirms that gravitational effects are not just felt, but radiated across the universe. The story of gravitational waves continues. Each detection offers opportunities for further tests. Are they propagating precisely at light speed? Do their polarization patterns match predictions? So far, all observations agree with general relativity, with no deviations. This tight conformity reinforces Einstein's century-old theory and constrains alternative models, ruling out many modifications. Some scientists view gravitational waves as a probe of the universe's earliest moments. During the inflation epoch after the Big Bang, it's hypothesized that primordial gravitational waves were produced, imprints of the universe's infancy. Detecting these would open a new window into moments just fractions of a second after the universe's birth, further testing Einstein's gravity at the most fundamental level. The field of gravitational wave astronomy is just beginning. Upgrades and new detectors, such as Virgo in Italy, Kagra in Japan, and the upcoming Einstein telescope, will allow detection of a wider array of sources. Each new observation will test and refine our understanding of gravity, making our conceptual framework more precise and profound. In the cosmic symphony, gravitational waves are the universe's own melody, initially hidden due to limited instrument sensitivity. Their discovery has transformed a theoretical prediction into a fundamental pillar of physics. It's a confirmation that rewrites textbooks and reshapes our understanding of reality, anchoring Einstein's legacy in the fabric of the cosmos. As exploration continues, studying black hole mergers, neutron-star collisions, and echoes from the universe's dawn, gravitational waves remain our most direct messengers, whispering secrets about the shape, origin, and fate of the cosmos. Their detection not only affirms Einstein's theory, but also prompts fresh questions. What other mysteries lie in space-time's subtle curvature? How deep do the secrets of gravity run through the universe's fabric? By tuning into these cosmic ripples, we listen to the universe's most fundamental song, composed by the very curvature of space-time itself. Astronomical observation plays a crucial role in understanding gravity by serving as the universe's natural laboratory, an environment where the fundamental principles of matter and space-time are tested and refined. Unlike terrestrial experiments, observational astronomy grants us access to phenomena beyond human lifespans and environments impossible to replicate artificially. By analysing light, gravitational signals, and other radiation from distant objects, astronomers decipher how gravity shapes the universe. Historically, curiosity about gravity stemmed from planetary motions and celestial mechanics. Early astronomers used telescopes and mathematical models to chart planetary, lunar, and stellar orbits. Tycho Brahe, Copernicus, Kepler, and Newton studied planetary paths, noting their orderly motion suggested underlying forces. Kepler's laws, derived from Mars observations, indicated a controlling force. Newton's law of universal gravitation formalized this, describing how masses attract each other, affecting orbital motion across scales. Astronomical observations are essential to testing gravitational theories across wide scales, from our solar system to distant galaxies. Newtonian physics describes planetary motions well, but less so for larger, faster, or more massive systems like galaxy clusters. Observations of stellar rotation speeds in galaxies reveal discrepancies. Stars in outer regions move faster than visible matter predicts, implying unseen mass, dark matter, that exerts gravity yet remains invisible. Such findings challenge and shape our understanding of gravity and matter. Further, studying galactic motions helps infer mass distribution, including dark matter, through effects like galaxy rotation curves, velocity dispersions, and clustering. Observations of galaxy clusters through X-ray emissions, gravitational lensing, and velocities demonstrate visible matter accounts for only part of the mass needed for gravitational stability. These investigations support dark matter hypotheses, interacting gravitationally but not electromagnetically detectable directly. Gravitational lensing exemplifies how observational science probes spacetime's fabric influenced by gravity. light passing near a massive object, like a galaxy or cluster, bends according to Einstein's general relativity, distorting background images. Analyzing such distortions yields detailed mass maps, revealing both visible and unseen mass. Lensing observations provide strong evidence for dark matter, since visible matter alone cannot account for observed effects. Detecting gravitational waves further exemplifies observational advances. Predicted by Einstein's general relativity, these ripples in space-time emerge when massive objects, like black holes or neutron stars, merge, producing signals detectable by instruments like LIGO and Virgo. These detections confirm gravity's dynamic, wave-like nature, testing Einstein's predictions in extreme fields and opening new observation windows. They deepen our understanding of gravity under intense conditions and challenge existing theories. Astronomical observations also underpin insights into the universe's accelerated expansion. Measurements of distant Type Ia supernova, standard candles, reveal that the universe's expansion not only continues but accelerates. This suggests a repulsive component of energy, dark energy, affects the cosmos on large scales. Without precise measurements of supernova brightness, redshift, and cosmic microwave background signals, understanding the universe's evolution and gravity's role would be impossible. Similarly, the cosmic microwave background, CMB, residual heat from the Big Bang, offers critical clues about matter distribution and gravity's influence on structure formation. Satellite missions like COBE, WMAP, and Planck measure tiny temperature variations across the sky, enabling us to trace how gravity shaped initial fluctuations into galaxies, clusters, and superclusters. These observations support and refine theories of gravity's early universe role. On smaller scales, studying dense objects such as black holes, neutron stars, and pulsars provides tests for gravitational physics under extreme conditions. Pulsars serve as cosmic clocks due to their precise rotational periods, allowing measurement of gravitational effects like redshift and time dilation predicted by general relativity. Monitoring pulsar binaries has indirectly tested gravitational wave emission, confirming Einstein's theories with remarkable accuracy. The direct detection of gravitational waves from black hole or neutron star mergers has revolutionized astrophysics. These waves encode information about spacetime near these objects and offer insights into extreme gravity physics. Continuous observations, complemented by electromagnetic signals, confirm gravitational law universality, refine models, and could reveal physics beyond Einstein's framework. Additionally, understanding large-scale structure formation driven by gravitational instability is fundamental. Surveys of galaxy distribution via optical, radio, and infrared telescopes allow us to study how matter clumped over billions of years, forming filaments and voids in the cosmic web. These data inform simulations and models, testing gravity's behavior over cosmic time and scale. Advances in observational technology, space telescopes like James Webb, ground-based observatories, and radio arrays enhance our ability to observe gravitational phenomena. High-resolution imaging, spectroscopy, and time-domain surveys detect subtle effects of gravity, such as frame dragging or lensing on small scales, or pulsar timing variations. Such data continue to challenge and refine gravitational theories. The universe acts as an intricate, changing testing ground for gravity's laws. Every photon, gravitational wave, or cosmic signal contains information about mass-energy distribution and its interaction within spacetime. By collecting, analyzing, and interpreting these signals, astronomers weave a coherent story of gravity's influence from planetary systems to the observable universe's vast structure. Without this meticulous observational process, our understanding of gravity would be superficial or incomplete. Tracking galaxy rotations, detecting gravitational waves, studying cosmological background radiation, and observing extreme objects are key to unraveling gravity's nature. Each new observation challenges existing ideas, inspires new theories, and provides critical clues to a unified physics understanding. In essence, astronomy is foundational to gravity study. Observations turn equations into phenomena, confirming or refuting theories, and opening avenues for revolutionary insights into spacetime and matter. Our grasp of gravity depends on the universe's signals, each a piece of a puzzle guiding us toward fundamental truths about space, time, and matter. The cosmos's grand display beckons us to observe, understand and comprehend gravity's profound role beneath its vast canopy. Satellite measurements have fundamentally transformed our understanding of gravity, turning it from a primarily theoretical concept into an observable and measurable force influencing Earth and the cosmos. Before satellite technology, our knowledge of gravity came mainly from ground experiments, classical mechanics, planetary observations, pendulums, and seismic studies, each providing insights but limited in scope. These methods couldn't capture gravity's subtle variations over large regions or in complex environments, such as space or deep within planetary interiors. Satellites revolutionized this understanding by offering high-precision, global-scale measurements that reveal gravity's intricacies in unprecedented detail. The development of satellite technology began during the Cold War space race with Sputnik's launch in 1957, initiating space-based observation. But it was through specialized scientific missions that our grasp of gravity deepened. Artificial satellites equipped with advanced instrumentation allowed scientists to monitor gravity's influence on orbital dynamics with precision. Accelerometers, laser ranging systems, and onboard sensors became essential for detecting tiny gravitational influences that ground measurements couldn't resolve, especially over large or inaccessible regions. One of the most groundbreaking advancements was the launch of gravity mapping satellites, like the Gravity Recovery and Climate Experiment GRACE in 2002. Comprising two satellites orbiting about 200 kilometers apart, GRACE used laser interferometry to measure their distance with extraordinary precision, down to micrometers. As they crossed various Earth's gravitational regions, shifts in their relative positions due to gravitational anomalies were detected and mapped. This method enabled scientists to observe tiny gravity variations caused by differences in density within Earth's crust and mantle, revealing unseen structures deep beneath. GRACE's data revolutionized Earth science. It tracked groundwater depletion in drought-prone areas, providing critical information for water resource management. It also monitored seismic activity, volcanic eruptions, and tectonic shifts by detecting localized gravity variations over time. These observations improved models of Earth's interior, identifying density anomalies, subducting tectonic plates and mantle plumes, offering a window into processes shaping our planet. Additionally, the data refined our understanding of Earth's shape, rotation, and moments of inertia, parameters vital for navigation, satellite orbit prediction, and understanding internal dynamics. Building on GRACE's success, the follow-up mission, GRACE-FO, launched in 2018, enhanced resolution and sensitivity. Its advanced instruments allowed scientists to observe subtle changes in Earth's ice sheets, tracking mass loss in Greenland and Antarctica caused by climate change. This data proved essential for refining sea level rise models, enabling more accurate predictions of future impacts on coastal regions. It also shed light on how melting ice alters Earth's gravitational field, affecting rotation and orbit, phenomena crucial for climate science and space navigation. The European Space Agency's Gravity Field and Steady-State Ocean Circulation Explorer, GOC, launched in 2009, used a highly sensitive gradiometer to map gravity gradients, variations over small distances, with detail. GOCI revealed features such as subduction zones, mantle plumes, and variations beneath tectonic plates, advancing understanding of geophysical processes like plate tectonics, volcanic activity, and mountain formation. These insights are vital for both fundamental geoscience and practical applications like navigation, satellite orbit prediction, and disaster preparedness. Beyond Earth, satellites have been pivotal in testing fundamental physics, especially Einstein's general relativity. Gravity Probe B, launched in 2004, used ultra-precise gyroscopes in orbit to measure space-time curvature caused by Earth's mass. Its results confirmed predictions of frame dragging and geodetic precession with high accuracy, demonstrating that space-time responds to mass and energy. These measurements provided crucial support for Einstein's theory and continue to test the limits of gravity and space-time, probing potential deviations that could reveal new physics beyond current models. Satellites also contribute indirectly to gravitational wave research. Missions like the proposed Laser Interferometer, Space Antenna, LISA, aim to directly detect gravitational waves from black holes, neutron stars, and other cosmic phenomena. Currently, satellite data helps map the universe's gravitational background, which could eventually reveal interactions hidden from electromagnetic observations, offering new insights into the universe through space-time ripples. Practical applications of satellite gravity measurements underpin modern technology. The Global Positioning System, GPS for example, accounts for local gravitational variations to provide accurate positioning. Without considering gravity's influence on satellite orbits and relativistic effects, GPS would be unreliable. Satellite data improves navigation for civilian use, military operations, aircraft guidance, and autonomous vehicles. It also aids asteroid tracking, space mission planning, and resource exploration, ensuring safety and efficiency in our expanding space activities. Together, these satellite measurements have dramatically expanded our grasp of gravity, transforming it into a richly detailed, observable phenomenon. They have revealed Earth's internal structures, monitored climate-driven mass movements, and provided critical test of Einstein's theories. Satellite data connects gravity's role across scales, from galaxy behavior to ice sheet changes, bridging observational science and theoretical physics. This progress deepens understanding and impacts practical applications, improving navigation, disaster response, climate prediction, and broadening our exploration of the universe's fundamental forces. Satellites have opened a window into gravity's true nature, turning it from an invisible force into a dynamic, measurable reality woven into the universe's fabric. Their ongoing advancements challenge our understanding, revealing new complexities and hinting at secrets yet to be uncovered in fundamental physics. Today, gravity is no longer just an apple falling. It's a phenomenon with depth, nuance, and relevance that extends throughout the cosmos. Despite significant advances in understanding gravity since Newton and Einstein, the universe continues to present mysteries and anomalies that challenge our current models. These phenomena are not mere curiosities, but fundamental puzzles that threaten to upend or extend our understanding of gravity, pointing toward new physics beyond Einstein's equations and Newton's laws, a potential paradigm shift that could reshape our comprehension of the cosmos. One of the most compelling anomalies involves galaxy rotation curves. Observations show stars orbit galactic centers at speeds that defy explanation, if only visible matter is considered. Classical physics and Newtonian gravity suggest stars on the outskirts should orbit more slowly, like planets in our solar system, Mercury orbiting more slowly than Earth, for example. Yet, astronomers see outer stars moving at high velocities, indicating unseen mass. This discrepancy led to the hypothesis of dark matter, an elusive, non-luminous matter that interacts gravitationally, but neither emits nor absorbs light. Dark matter appears to outweigh visible matter by roughly 6 times, forming a gravitational halo that stabilizes galaxy rotations. While this explains rotation curves well, the true nature of dark matter remains a mystery. Despite extensive experiments and detectors, direct detection has eluded scientists, prompting some physicists to question whether gravity behaves differently on galactic or cosmic scales, an idea that would require modifications to Einstein's theory or entirely new frameworks. Another profound puzzle is the universe's accelerating expansion. Observations of distant Type Ia supernovae reveal that not only is the universe expanding, but it is doing so at an increasing rate. This acceleration implies a mysterious form of energy, dark energy, that makes up about 68% of the universe's total energy content. Unlike ordinary matter and energy, dark energy acts as a repulsive force, driving galaxies apart faster over time. The simplest explanation involves Einstein's cosmological constant, a fixed energy density inherent to space. However, the observed values are much smaller than theoretical predictions, leading to the cosmological constant problem. Alternative theories suggest dynamic dark energy or modifications to gravity that become significant on cosmic scales, effectively changing how gravity operates over vast distances or high energies. These models are tested with data from the Cosmic Microwave Background (CMB), large-scale galaxy surveys, and gravitational lensing, but a complete understanding remains out of reach. Gravitational lensing further highlights anomalies. Einstein's general relativity predicts how massive objects bend light, but measurements often indicate more lensing than visible matter can produce. This excess supports dark matter, but also hints at potential modifications to gravity itself. Some propose gravity might become stronger or weaker, depending on the environment or scale, especially across cosmic distances. These ideas challenge Einstein's well-validated theory within our solar system, but less so at larger scales. Subtle deviations in lensing patterns occasionally appear, prompting physicists to explore alternative gravitational theories like tensor vector scalar (TVES) models or modified Newtonian dynamics (MOND), which attempt to explain galaxy rotation without dark matter but face their own issues. Locally, phenomena near black holes probe gravity's limits. Matter spiraling into black holes and gravitational waves from black hole mergers provide natural labs for testing Einstein's predictions. Recent detections by LIGO and Virgo have aligned with theoretical models, but increased sensitivity could uncover deviations, such as altered polarization states or dispersion, that might reveal new physics or extra dimensions. These investigations could force us to re-evaluate spacetime's fabric. The study of black holes, especially the regions near the event horizon, also raises unresolved issues like the black hole information paradox, whether information falling into a black hole is lost or preserved in a quantum sense. Resolving these paradoxes might require radically new theories unifying quantum mechanics with gravity. On the quantum scale, gravity's behavior remains mysterious. The incompatibility of quantum mechanics with general relativity is one of the deepest puzzles in physics. Both theories work well within their domains, quantum mechanics for the subatomic and general relativity for the large universe, but break down at black hole singularities or during the universe's earliest moments. The search for a quantum theory of gravity, via approaches such as string theory or loop quantum gravity, continues. Experimental evidence remains limited, but future tools, more sensitive gravitational wave detectors, high-energy colliders or quantum sensors, may offer insights. Theoretical concepts like gravitons, the hypothesized particles that mediate gravity, are central. Detecting these particles could bridge quantum and classical views, transforming our understanding of the universe's fundamental structure. Further anomalies include the flyby anomaly, unexpected small increases in spacecraft velocity during Earth flybys, baffling scientists for decades. Although attributed to measurement errors or atmospheric effects, the anomalies persist, suggesting unrecognized physics or subtle effects of modified gravity. Similarly, pulsars, rapidly rotating neutron stars, serve as cosmic clocks with extraordinary stability. Tiny deviations in pulsar timing, despite plausible astrophysical causes, could also hint at gravitational effects beyond general relativity or dark matter influences. These small anomalies motivate ongoing research, suggesting gravity may behave differently under specific conditions or regimes yet untested. Efforts to detect gravitons or observe quantum effects of spacetime continue. So far, no direct evidence has been found, but novel approaches like quantum sensors or experiments probing spacetime's quantum nature hold promise. Microscale deviations from expected gravitational behavior could reveal that gravity is emergent from deeper, more fundamental phenomena. These anomalies emphasize that our understanding of gravity is incomplete. They serve as clues that Einstein's equations might only be approximations within a broader framework yet to be discovered. Could there be hidden particles, unknown forces, or principles waiting to be uncovered? Might gravity be emergent from microscopic degrees of freedom? Are the current theories just the surface of a deeper structure of space-time? These questions drive ongoing research and inspire new generations of physicists. The universe continually reminds us that what we know is provisional. Every anomaly or unresolved signal is both a challenge and an invitation for scientific revolution. Gravity may be only a chapter in a larger story, one that will reveal profound truths about spacetime's fabric. Pursuing understanding with curiosity and humility, acknowledging that gravity might be a window to even more astonishing realms, continues. The quest to decode gravity's true nature proceeds, with the universe holding many surprises that could reshape our worldview for generations. Those 24 words exactly. Imagine standing on a hilltop feeling the gentle pull that keeps you grounded. This is the classic understanding of gravity. For centuries, gravity was seen as a force, a mysterious invisible tug exerted by one object on another. Sir Isaac Newton formalized this idea in the 17th century, revolutionizing our understanding of the universe. Newton's law of universal gravitation states that every mass attracts every other, with a force proportional to their masses and inversely proportional to the square of the distance between them. Think of it as a cosmic dance where each partner pulls on the other, weakening as they drift farther apart. Mathematically, this is expressed as affirmed, F-I-A-W-S-G-I-F-R-A-C-M-R-E-N. M2 a 2-Rlan, where Fn is the force, Gn the gravitational constant, and M2 the masses, and Rn the distance. In Newton's framework, gravity acts instantaneously. Any change in mass distribution is felt immediately, regardless of distance. If the Sun suddenly vanished, Earth would instantly leave its orbit because gravitational influence would cease instantly. This view aligned with the mechanical worldview of Newton's time. Forces acted along the line connecting objects and were transmitted through an invisible medium called ether, once thought to carry forces through space. In this classical picture, gravity was a fundamental force, like magnetism or electricity, calculable and predictable with laws. It governed planetary motion, kept satellites in orbit, and explained moon orbits around planets. Planets were regarded as massive particles moving along predictable paths, influenced only by gravity from larger bodies like the Sun or Earth. A key feature of classical gravity is its long-range nature. It extends infinitely, diminishing with the square of distance. Unlike nuclear or electromagnetic forces, gravity creates a universal, space-permeating field. Newton's universe, however, assumed this field was instantaneous. Any change in mass distribution would be felt everywhere immediately. Over centuries, this simple idea matched observations and experiments. Newton explained tides as the moon's gravitational pull on oceans, not merely mechanical effects. He modelled celestial motion with remarkable accuracy, replicating planetary orbit measurements. These successes reinforced the classical view of gravity as an unseen, omnipresent force. Questions arose. What exactly is this force? How does it travel? Why does it act instantaneously? These questions persisted for over 2 centuries. The notion of action at a distance, forces acting across empty space without a medium, grew less plausible. Physics began favouring explanations rooted in fields and local interactions over mysterious attractions. In the 19th century, Maxwell's electromagnetic theory introduced the concept of fields as standard tools to understand forces, local interactions mediated by disturbances travelling at finite speeds, namely the speed of light. This shift cast doubt on the classical instantaneous notion of gravity. Early 20th century developments, especially Einstein's general relativity, transformed this view. Instead of a force pulling objects together, Einstein proposed that mass and energy curve space-time, the fabric of the universe, making it a dynamic, geometric entity. Objects follow straight paths, geodesics, in this curved space-time which appears as orbits or falling objects to us. Does this mean gravity is no longer a force? Not exactly. Einstein's picture reinterprets gravity as a manifestation of curved space-time, not a force acting across space. Yet for many practical purposes, Newtonian gravity remains accurate. When gravitational fields are weak and velocities low, Newton's laws suffice. However, the classical model has limitations. It cannot explain phenomena like gravitational lensing, the bending of light by massive bodies, or the precise behaviour of planets in strong fields. It also doesn't account for the fact that gravitational influences seem to propagate at the speed of light, not instantaneously as Newton proposed. In extreme situations such as near black holes or the early universe, classical gravity becomes inadequate. Modern physics recognises gravity within a quantum framework. Reconciling quantum mechanics with general relativity remains a major challenge. The classical picture is incomplete, especially at very small scales or high energies. Despite these limitations, Newtonian gravity remains widely used in engineering, astronomy, and daily life. It underpins satellite orbits, space mission planning, and planetary mechanics. Its elegant, intuitive nature makes it accessible and useful in technology. At its core, the classical picture is simple. Masses exert an attractive force pulling objects toward each other, governed by straightforward laws. It captures the essence of universal gravitation in a human-accessible form, forming a foundation for scientific and technological pursuits. Beneath this simplicity, the idea suggests a universe where gravity isn't just a tug but part of a deeper geometry, an energy dance woven into spacetime's fabric. Physicists continue exploring gravity's true nature, revealing a complex interplay of geometry and energy that goes far beyond Newton's initial ideas. The classical understanding remains a crucial stepping stone. It offers an elegant, practical framework for understanding the universe at human and planetary scales. It underpins many technological advances, yet hints at deeper truths that challenge our understanding of reality. Unraveling gravity's mystery may lead to discoveries beyond the classical force concept, possibly revealing its fundamental link to space-time geometry and quantum phenomena. Such insights could revolutionize physics and provide new windows into the universe's true nature. In summary, the classical view sees gravity as an invisible, attractive force acting at a distance, governed by simple, elegant laws. It is observable in daily phenomena, yet it's only a piece of a much deeper, more complex picture that modern physics continues to explore. Physicists seek a quantum theory of gravity because, despite the remarkable successes of Einstein's general theory of relativity, the two pillars of modern physics, general relativity and quantum mechanics, remain fundamentally incompatible at their core. To truly understand the universe at its most profound level, we need a framework that can unify gravity with the quantum world. The quest for a quantum theory of gravity isn't just about adding another piece to the puzzle, it's about fundamentally reconciling how we understand the fabric of space, time, and matter. At everyday scales and in most astrophysical phenomena, Einstein's theory of relativity reigns supreme. It beautifully describes how massive objects curve space-time and how gravity influences the motion of planets, stars, and even light. It's a classical theory. Think of it as a smooth, continuous fabric that does not incorporate the probabilistic nature of quantum mechanics. Quantum mechanics, on the other hand, governs the behavior of particles at the tiniest scales, atoms and subatomic particles, where nature's laws are inherently uncertain, discrete, and governed by probabilities. But when we turn to the universe's most extreme environments, black holes, the Big Bang, or the birth of the cosmos, these two descriptions collide. Inside a black hole's singularity, the density of matter and the curvature of space-time become so intense that classical descriptions break down. Our current theories offer no reliable answers at these points. They become predictions of impossible infinities, places where the mathematics no longer make sense and the laws of physics seem to lose their meaning. This incompatibility isn't just an academic issue, it's a profound obstacle to understanding the origins and ultimate fate of the universe. Physicists are haunted by the idea that a singularity, where existing theories collapse, might conceal new, deeper laws that could be glimpsed only through a quantum theory of gravity. To explore what really happens at the heart of a black hole, or during the universe's earliest moments, requires a theory that seamlessly integrates quantum physics with Einstein's gravity. Imagine the universe at the quantum level. Space and time might not be the smooth, continuous fabric that Einstein described. Instead, they could be composed of discrete quantized units, tiny fundamental building blocks known as quanta of space-time. Just as atoms form matter, these fundamental quanta would form the very fabric of space and time, vibrating and interacting according to quantum principles. This perspective could resolve the infinities that plague current models by providing a natural cutoff at the smallest scales, and would likely open the door to understanding phenomena we can't comprehend with classical theories alone. Furthermore, recent developments in theoretical physics, such as string theory and loop quantum gravity, are driven by the ambition to develop these quantum theories of gravity. String theory proposes that all particles and forces, including gravity, are vibrations of tiny, one-dimensional strings, unified in a higher dimensional space. Loop quantum gravity, on the other hand, attempts to quantize space-time itself, suggesting it has a granular structure made of finite loops woven into the fabric of the cosmos. Both approaches aim to describe how gravity behaves when quantum effects become significant, especially under extreme conditions. These theories are not just mathematical exercises. They have profound implications for understanding the origins of the universe. For instance, the Big Bang may be better described not as a singular event of infinite density, but as a bounce, a transition from a prior quantum state, resolving the paradoxes of initial singularities. This could rewrite our entire narrative about the beginning of everything, showing that the universe's birth was a quantum event woven into the fabric of space-time itself. Beyond black holes and the Big Bang, a quantum theory of gravity might shed light on the nature of dark matter and dark energy, which together comprise about 95% of the total mass-energy content of the universe, yet remain mysterious. Could these phenomena be manifestations of quantum gravitational effects? Or could the fabric of space-time itself be more dynamic and complex than currently believed? Some theories suggest that quantum fluctuations at cosmic scales might influence the expansion of the universe, lending new insights into these cosmic enigmas. Another compelling reason to pursue quantum gravity is to deepen our understanding of fundamental symmetries and the fabric of reality. Classical gravity is deterministic. Given initial conditions, the future can be predicted, but quantum mechanics introduces fundamental uncertainty. How do these coexist? Developing a quantum theory of gravity could reveal new symmetries and principles that govern the universe at its deepest level, potentially leading to new physics that could revolutionize our understanding of reality. Quantum gravity also promises practical dividends. Although it's primarily a theoretical pursuit, unifying the laws of physics might lead to breakthroughs in technologies we can't yet envision, much like how understanding electromagnetism led to electricity and modern electronics. The quest to understand space-time at the quantum level could yield new insights into quantum computing, information theory, and the nature of consciousness, blurring the lines between physics, philosophy, and technology. Importantly, the search for a quantum theory of gravity exemplifies the spirit of scientific exploration, our relentless drive to understand the cosmos not just as it appears, but as it truly is at its most fundamental level. It challenges us to rethink our assumptions, push the boundaries of mathematics and experimental physics, and confront the limits of human knowledge. Each step forward in this quest brings us closer to revealing the universe's deepest secrets and unifies the diverse phenomena we observe, from subatomic particles to galaxies, under a single, coherent framework. To sum it up, physicists are motivated by the desire to unify the two great theories of the 20th century into one overarching description. It's about creating a consistent, all-encompassing framework that can describe gravity at the quantum scale, resolve the mysteries of black holes, clarify the origins of the universe, and perhaps unveil new principles of nature yet to be discovered. It's an ambitious, groundbreaking pursuit, one that stands at the frontier of modern physics, promising to transform our understanding of reality itself. When contemplating the universe's tiniest scales, distances so minuscule that current physics begins to break down, the challenge of unifying gravity with quantum mechanics becomes evident. For centuries, gravity has been understood as an observable, classical force, the apple falling from a tree, the moon's gravitational pull, planets orbiting stars that we can measure, observe, and feel directly. Yet, at the Planck scale, approximately 10 to the minus 33 centimeters, space-time itself appears to become fuzzy, granular, and inherently quantum in nature. Under such conditions, the smooth, continuous fabric of space-time described by Einstein's general relativity ceases to suffice. Instead, various approaches aim to reconcile Einstein's classical theory with the probabilistic, discrete nature of quantum mechanics. These efforts, underpinned by distinct philosophies and mathematical frameworks, seek a coherent theory of quantum gravity. One of the most studied frameworks is string theory, which posits that the fundamental constituents of reality are not zero-dimensional point particles, but one-dimensional vibrating strings. Different vibrational modes correspond to different particles: electrons, quarks, photons, and gravitons. String theory inherently includes gravity because one vibrational state represents the graviton, the hypothetical quantum carrier of the gravitational force. It also implies extra spatial dimensions beyond the familiar 3, up to 10 or 11, most of which are compactified and hidden at scales too small to detect. These extra dimensions provide a rich landscape where strings vibrate and interact, and quantum gravity naturally emerges from their dynamics. Despite its elegance and unifying potential, string theory faces challenges. Its characteristic energy scales are near the Planck energy, far beyond current experimental reach, making direct validation difficult. Moreover, it features an enormous landscape of possible solutions, estimated at 10⁵ vacua, which implies an almost limitless number of possible universes. This multiverse complicates making definitive predictions and raises philosophical debates about falsifiability. Nonetheless, string theory's deep mathematical structure and potential to unify all particles and forces continue to inspire research and developments in theoretical physics. Another prominent approach is loop quantum gravity, LQG, which adopts a different philosophy. Instead of extending into higher dimensions or modeling particles as strings, LQG attempts to quantize space-time itself directly. It constructs a quantum geometry where space is woven from discrete loops, fundamental excitations called spin networks, that form a granular, combinatorial structure. These loops produce quantized values for area and volume, implying that space at the Planck scale is not continuous, but composed of finite, indivisible chunks. In this view, the classical smooth spacetime emerges as an approximation at large scales, while at the smallest scales, the fabric of space resembles a network of quantum threads. LQG's simplicity and reliance solely on the geometry of spacetime make it appealing. It does not invoke extra dimensions or new particles. It offers promising solutions to classical singularities, such as black hole cores and the Big Bang, suggesting quantum effects could replace infinities with quantum bounces, potentially resolving long-standing problems. Despite these positives, LQG remains incomplete. It has yet to develop a full unified quantum field theory that combines all matter and forces. Predictions to date are difficult to test directly, but physicists hope observational signatures, such as specific imprints on the cosmic microwave background or gravitational wave spectra, may someday serve as tests. Asymptotic safety presents a different conceptual approach. Instead of adding new entities, it examines gravity's behavior at high energies using the renormalization group, tools from quantum field theory concerned with how physical parameters change with energy scales. The core idea is that gravity might have a non-Gaussian fixed point, a stable point in its renormalization flow, where it becomes scale invariant at high energies. This fixed point would ensure the theory remains predictive and consistent at all energy scales, despite gravity's non-renormalizability and perturbative approaches. Essentially, gravity could be safe at high energies because its properties become fixed and controlled. Research into asymptotic safety involves intricate mathematics to identify these fixed points and determine if the theory remains finite and predictive. If confirmed, this implies quantum gravity could be formulated within the familiar four-dimensional spacetime without exotic particles or extra dimensions, providing an elegant solution to long-standing mathematical issues. Although still largely theoretical, some initial studies and models support the existence of such a fixed point, making asymptotic safety a promising avenue for further research. Beyond these frameworks, the holographic principle and STS, anti-de Sitter, conformal field theory, AD-CFT correspondence, originating from string theory, suggest a radically different view. That gravity and spacetime might be emergent phenomena rooted in lower-dimensional, non-gravitational quantum theories. The holographic principle posits that all information contained within a volume can be encoded on its boundary, akin to a hologram. In the best understood realization, the AD-CFT correspondence, gravity in a higher-dimensional anti-de Sitter space, is dual to a conformal field theory without gravity on its lower-dimensional boundary. This duality allows physicists to study complex quantum gravitational phenomena using quantum field theories that are better understood. It has provided critical insights into black hole entropy, information paradoxes, and the deep links between quantum entanglement and spacetime. Some scientists explore emergent gravity as a more radical paradigm, which proposes that gravity is not fundamental but arises from quantum entanglement and information flow at microscopic scales. Based on thermodynamic and informational principles, emergent gravity suggests that the observed attraction of masses is similar to temperature and pressure emerging from the collective behavior of underlying microscopic degrees of freedom. Much like temperature arises from molecular motions in gases, while still largely conceptual, this idea has the potential to revolutionize our understanding of spacetime, connecting quantum information theories with gravitational phenomena and possibly offering new paths toward a quantum theory of gravity. Causal dynamical triangulations, CDT, offers a lattice approach, constructing quantum spacetime from simple building blocks arranged causally, preserving cause and effect sequences. By discretizing spacetime into fundamental simplices that respect causality, researchers aim to recover a smooth four-dimensional universe at large scales from underlying quantum, combinatorial structures. Computational simulations explore how classical spacetime emerges from these quantum geometries, seeking to reconcile quantum discreteness with macroscopic continuity. Although experimental confirmation remains distant, CDT provides a promising computational model to test ideas about quantum spacetime structure and dynamics. Collectively, these approaches aim for a unified, consistent, and testable quantum theory of gravity, reconciling classical and quantum worlds. Each offers unique insights, some rooted in particles, strings, and higher dimensions, others in quantized geometry, emergent phenomena, or holography, and all face profound mathematical and conceptual hurdles. The quest remains open, with no universally accepted theory. Many avenues remain unexplored. What makes this pursuit so compelling is that it probes the very nature of reality, questions about what space and time truly are, how the universe began, and the universe's fundamental fabric. Understanding quantum gravity could resolve paradoxes surrounding black holes and the Big Bang, leading to clearer pictures of the universe's earliest moments. These efforts push the boundaries of human knowledge, inspiring new mathematics, physics, and philosophy, deepening our understanding from the smallest scales to the largest structures. The search for quantum gravity remains one of the most profound scientific quests, driven by curiosity and the desire to understand the universe's deepest secrets. Imagine a universe woven from tiny, vibrating strings too small to see, but holding everything together. That's the essence of string theory's view of gravity. For centuries, humans have sought a unified picture of the forces governing the cosmos, and string theory offers an elegant yet complex framework that might achieve this. Traditionally, physics divides the universe into two main pillars: quantum mechanics, describing particles at tiny scales, and general relativity, explaining gravity and spacetime at large scales. These theories work well within their domains, but clash when trying to understand phenomena where quantum effects and gravity are significant, like black holes or the universe's birth. This disconnect fuels the search for a theory of everything. String theory proposes a radical idea. Fundamental particles, the electrons, photons, gluons, are not point-like dots but tiny, vibrating strings. Like a cello string producing different sounds based on vibrations, each particle's properties, mass, charge, spin, arise from the vibrational pattern of the string. How does this relate to gravity? Interestingly, in this framework, one vibrational mode corresponds naturally to a hypothetical particle called the graviton, which is thought to mediate quantum gravity. Unlike modes that produce known particles, the graviton appears as an inherent feature of the string's spectrum. As a result, gravity isn't an external force acting upon particles, it's embedded in the fabric of reality, encoded in the vibrations of these strings. This shift changes our perspective. Instead of viewing gravity as a mysterious curvature of spacetime caused by mass and energy, Einstein's geometric picture, string theory suggests gravity emerges from quantum vibrations of fundamental entities. These include the graviton, mediating gravitational interaction at the quantum level, similar to photons in electromagnetism. In classical physics, gravity is an effect, a bending of spacetime, while in quantum physics, forces are transmitted by exchange particles. String theory unifies these views by proposing that the graviton is just one vibration mode among many, woven into the very strings themselves. This unification is a long-standing goal, a quantum theory of gravity seamlessly integrated with the quantum mechanics of particles and forces. String theory's approach also helps resolve long-standing mathematical issues. At very high energies, traditional theories encounter infinities, mathematical nonsensicalities. String theory, with its extended objects instead of point particles, spreads out interactions over a tiny, finite scale, softening these infinities and making calculations more manageable. This framework reveals a beautiful harmony. Point particles of the standard model are replaced by strings that wiggle and vibrate, naturally giving rise to matter and force-carrying particles, including the graviton. It's as if the universe's blueprint is a cosmic symphony, each particle corresponding to a different pattern of string vibrations. Furthermore, string theory incorporates extra dimensions, beyond our familiar 3 of space and 1 of time, often 10 or 11 in total. These hidden dimensions are compactified or curled up so tightly they're undetectable. Their shape and size influence how strings vibrate, affecting particle properties and force strengths. The structure of these dimensions can impact the strength of gravity in the universe's fabric, hinting at connections between the microscopic and the cosmic. A fascinating aspect is how string theory bridges quantum phenomena and the geometric picture of general relativity. In some formulations, gravity appears as an emergent phenomenon, a collective effect of many string vibrations rather than a fundamental force. This idea suggests space-time itself could emerge from more fundamental quantum information encoded in strings, implying space-time might not be fundamental, but a large-scale emergent property of microscopic vibrations. Like any ambitious theory, string theory faces challenges. Its elegant mathematics hints at profound truths, but direct experimental evidence, such as detecting strings or confirming extra dimensions, is lacking. The energies needed to probe these tiny scales far exceed current technology, so scientists rely on indirect tests through consistency and implications. The perspective on gravity offered by string theory is revolutionary. Instead of treating gravity as an external mysterious force, it could be a manifestation of the universe's deepest strings vibrating in a multidimensional cosmic symphony. The classical curvature of space-time may be an emergent phenomenon arising from the collective behavior of quantum strings. This reimagining suggests that gravity isn't a mysterious external effect but an inherent property of the universe's fundamental building blocks. The idea that gravity arises from vibrations of underlying strings redefines our understanding. What once seemed like a geometric distortion might be a macroscopic illusion, a collective effect from microscopic vibrational dynamics. As we explore the universe's fundamental nature, string theory proposes that gravity is a melody woven into the fabric of reality itself. Instead of an outsider resisting our understanding, it becomes a fundamental part of the universe's most basic structure. The notion that this force is merely a whisper of strings vibrating at frequencies we're just beginning to understand invites profound rethinking, one that might ultimately elevate our understanding from classical geometry to quantum vibrational phenomena. The realization that gravity might be a summary of the universe's deepest strings vibrating in multidimensional space is radical. The classical picture of spacetime as a curved fabric could be an emergent illusion, arising from complex interactions of vibrating strings at microscopic scales. This view opens a realm where forces and particles are different expressions of a single underlying reality, woven together by vibrations. String theory doesn't just aim to unify gravity and quantum mechanics, it fundamentally redefines gravity. What we've long considered an external, mysterious force might actually be an innate property of the universe's smallest constituents. The geometric distortion of spacetime could be an emergent phenomenon, a large-scale reflection of microscopic string vibrations. This approach suggests our observed universe, with its curved spacetime and gravitational effects, might be a large-scale pattern emerging from an underlying quantum, vibrational pattern, an intricate cosmic symphony. The classical picture of gravity as a force caused by mass becomes a collective effect of countless tiny vibrations. In this framework, gravity as a geometric distortion is an illusion, arising from microscopic dynamics of strings vibrating in higher dimensions. These microscopic vibrations produce the large-scale curvature we observe as gravity, revealing a deeper layer of reality. By reimagining gravity as an intrinsic property of fundamental strings, string theory offers a revolutionary perspective. It suggests the force we've tried to understand for centuries may be nothing more than vibrational patterns in a multi-dimensional cosmic fabric. The familiar notion of gravity as a geometric curvature may be just an emergent effect, woven into the fabric of reality from the underlying symphony of vibrating strings. This insight invites us to think of the universe less as a stage where forces act upon matter, and more as a complex vibratory tapestry woven from the oscillations of fundamental strings. The fabric of space-time and gravity emerge from these microscopic patterns, a realization that could fundamentally change our understanding of the cosmos. As scientists explore these ideas, string theory beckons us to see gravity not as an outsider resisting our grasp, but as a melodic expression of the universe's most fundamental vibrations. It suggests our experience of gravity might actually be a whisper of strings vibrating in higher dimensions, hinting at a profound unity among forces and particles. In this view, the force we perceive as gravity isn't separate from the quantum world, but an intrinsic aspect of the universe's deepest structure. The classical geometric picture of spacetime might be a large-scale illusion, an emergent phenomenon arising from microscopic vibrational patterns in a higher dimensional cosmic symphony. In essence, string theory proposes that gravity is woven into the universe's most fundamental fabric, a direct consequence of the vibrations of tiny strings. Instead of a mysterious external force, it might be an internal property of these fundamental elements, a melody played across dimensions. This radical rethinking could one day lead us to a new understanding, uniting the quantum and the cosmic into a cohesive, vibrating whole. The quest to unify gravity with quantum mechanics is one of the greatest challenges in modern physics, and it's a puzzle that has confounded scientists for over a century. This challenge stems from the fundamental differences between the two theories, each successful in its own domain but seemingly incompatible when combined into a single framework. Quantum mechanics describes particles at the smallest scales, atoms and subatomic particles, where outcomes are probabilistic and quantities like energy and position are not always precise until measured. It has been extensively tested, underpinning technologies such as semiconductors, lasers, and MRI machines. Its features like superposition, where particles exist in multiple states simultaneously, are counterintuitive but experimentally verified. In contrast, general relativity models gravity as the curvature of spacetime, not as a force. Massive objects bend spacetime, which in turn guides the motion of matter. Einstein's equations have been validated through phenomena like planetary orbits and light warping. These theories work well in their respective realms: quantum mechanics in the microscopic world, and general relativity on macroscopic scales dominated by gravity. Problems arise when trying to unify them. The core conflict lies in their mathematical languages and conceptual frameworks. Quantum field theories, which describe electromagnetism and nuclear forces, assume spacetime is a fixed, smooth background. Gravity is different. Spacetime is dynamic, warping and evolving with mass and energy. Attempting to quantize gravity, treating gravitational fields as quantum particles called gravitons, leads to severe mathematical issues. Calculations produce infinities called ultraviolet divergences that are unmanageable, unlike in quantum electrodynamics where renormalization cancels infinities to produce meaningful results. Gravity's non-linear nature complicates matters further. The gravitational field itself carries energy and influences spacetime in complex ways. Applying straightforward quantum field theory techniques results in a non-renormalizable, inconsistent theory. At extremely small scales, on the order of the Planck length, spacetime is believed to break down into a more fundamental, possibly discrete structure. However, we lack experimental access to these scales, making direct tests impossible so far. Conceptually, the theories also clash. Quantum mechanics involves uncertainty and superpositions, particles in multiple states until measured. General relativity assumes a smooth, continuous spacetime with a well-defined geometry. So, questions emerge. How does a superposition of different spacetime geometries work? Can spacetime itself be in a superposition? These questions challenge our understanding of what geometry means at the fundamental level. Another major obstacle is the lack of experimental data. Though phenomena like black hole evaporation and spacetime near singularity suggest the need for a quantum theory of gravity, no direct measurements exist at the relevant energies, about 10 to the 33rd power higher than current accelerators can produce. Without experimental constraints, most theories are speculative, making it harder to select the correct approach. Physicists have proposed various models, each with challenges. String theory replaces point particles with vibrating strings, potentially unifying all forces, including gravity. But it demands extra spatial dimensions, sometimes as many as 10 or 11, and the vast landscape of solutions complicates making predictions. Loop quantum gravity takes a different approach, attempting to quantize spacetime directly. It predicts a granular, discrete structure at the smallest scales using loops of quantum geometry. While promising, it remains incomplete and uncertain whether it can recover known physics or yield testable predictions. Black hole physics exemplifies the clash of quantum mechanics and gravity. The black hole information paradox asks whether information is destroyed or preserved when matter falls into a black hole. Resolving this paradox requires a consistent theory combining quantum principles and curved spacetime, a goal that remains out of reach. Finding such a theory would clarify whether information truly vanishes or is somehow retained, challenging our understanding of quantum and gravitational principles. Moreover, deeper philosophical questions persuade scientists to seek a unified theory. Might spacetime itself be emergent from more fundamental quantum entities, or is spacetime fundamental and the challenge lies in discovering the right mathematical connection. These questions reflect the conceptual, technical, and philosophical hurdles that stretch our current knowledge. Unifying gravity and quantum mechanics is akin to assembling a puzzle with incompatible pieces, yet the complete picture is essential. We need to reconcile the smooth, fabric-like space-time of relativity with the probabilistic, jittery nature of quantum particles. Both theories are deeply verified within their domains, but integrating them into a single, consistent framework remains one of the greatest scientific pursuits of our time. Researchers continue exploring this uncharted territory. Each theoretical insight or experimental hint brings us closer to understanding. Approaches like string theory, loop quantum gravity, or novel ideas may eventually yield a harmonious fundamental theory of nature. The goal is to find that elusive unity, a comprehensive understanding that reveals the true nature of reality at the deepest level. This journey forces us to rethink what we know, expand our mathematical tools, and probe more profoundly into the universe and ourselves. The challenge is immense, but it promises revolutionary insights about the fabric of existence. Despite the roadblocks, progress is being made, and even failure advances understanding by highlighting what doesn't work. The pursuit of unifying gravity with quantum mechanics is not only a scientific challenge, but also a philosophical and conceptual one, an endeavour that tests the limits of human curiosity and ingenuity. Ultimately, the synthesis of these theories might appear as an elegant, simple framework, yet its realization requires overcoming profound technical challenges and reconciling competing visions of reality. As our understanding deepens, we might uncover new principles of nature, new states of matter, or even modifications to our ideas of space, time, and causality itself. The quest continues as we seek to complete the grand puzzle, revealing a more complete, unified picture of our universe, one that transcends current limitations and illuminates the fundamental nature of all existence. Imagine standing beneath a vast, stretched fabric, like a giant transparent sheet of silk pulled tight across the universe. When you place a heavy object, such as a bowling ball, onto this fabric, it creates a deep, curved indentation. Smaller objects like marbles nearby will roll toward the heavy object, not because there's some invisible force pulling them directly, but because of the curvature of the fabric itself. This analogy, while not perfectly accurate, captures how Einstein's general theory of relativity describes gravity as a distortion of the fabric of space-time. For centuries, the prevailing thought was that gravity was a force exerted at a distance, Newton's apple falling straight to the ground, feeling as if an unseen hand pulled it downward. But Einstein revolutionized that view by proposing gravity isn't a force in the traditional sense. Instead, it's a manifestation of space-time geometry. Mass and energy tell space-time how to curve, guiding motion. Objects move along the straightest possible paths, called geodesics, in a curved space-time. What we perceive as gravitational attraction is simply these objects following paths dictated by the shape of space and time around them. In Einstein's framework, space-time is like a four-dimensional fabric, 3 dimensions of space combined with time, that can be bent, warped, and stretched. When a massive body, like a star or planet, is present, it causes a deformation of this fabric. Think of space-time as a vast, transparent sheet. Placing a mass such as the Sun in the middle creates a deep well or well-like curvature. Mercury orbits the Sun not because of an invisible tether, but because it moves along the curved path shaped by this distorted space-time. That curvature acts like a landscape of hills and valleys, guiding planets along curved trajectories. Mathematically, Einstein expressed this with the Einstein field equations, relating the distribution of mass energy to spacetime's curvature. Unlike Newtonian gravity, which treats gravity as an instant force transmitted across space, Einstein's view shows changes in the gravitational field propagate at the speed of light. If the Sun suddenly disappeared, Earth wouldn't feel the loss of gravity immediately. There would be a delay corresponding to the time it takes for changes in curvature to propagate outward. This geometric approach to gravity leads to profound implications. It predicts phenomena Newton's laws couldn't account for, like the precise precession of Mercury's perihelion. Newtonian physics, remarkably accurate for many purposes, failed to explain Mercury's long-term orbit accurately. Einstein's equations corrected this, demonstrating gravity as a geometry rather than a force. Einstein's theory also shows that light is affected by gravity. Photons, massless particles of light, follow space-time curvature. When passing near a massive object, their paths bend, a phenomenon called gravitational lensing. This has been observed around the Sun and distant galaxies, confirming Einstein's predictions. Gravitational lensing helps astronomers study otherwise invisible objects like dark matter by observing how light from distant sources is warped by intervening mass. Another key prediction is the existence of gravitational waves, ripples in space-time caused by accelerating massive objects. These waves stretch and squeeze space-time as they pass, and their tiny distortions can now be measured with detectors like LIGO. In 2015, scientists detected gravitational waves from colliding black holes, opening a new window into the cosmos. Black holes are another remarkable prediction of Einstein's theory, regions of space-time where curvature becomes infinite, trapping everything inside. The core of a black hole forms a singularity, an edge of space-time where current physics breaks down. Surrounding it is the event horizon, beyond which nothing escapes. Black holes challenge our understanding of gravity, quantum mechanics, and reality itself, fueling ongoing research. Despite its successes, Einstein's general relativity isn't the final answer. It doesn't incorporate quantum mechanics, which governs the subatomic realm. Inside black holes and at the universe's earliest moments, Einstein's equations falter because quantum effects become significant. Physicists seek a quantum theory of gravity, string theory, loop quantum gravity, and others to unify Einstein's geometric perspective with quantum physics. No complete, experimentally confirmed theory exists yet. Even Einstein doubted aspects of his own theory later in life, pondering whether gravity might somehow emerge from deeper principles. The quest to understand gravity remains ongoing, complex, and full of mysteries. Exploring the fabric of reality is an ongoing challenge that pushes our perception of the universe. What makes Einstein's geometrical view compelling is how elegantly it unifies matter, energy, space, and time into a coherent framework. It suggests the universe isn't simply a stage but an active participant, its geometry influencing everything within. Gravity isn't just an invisible pull but a dance governed by the shape and structure of space-time. Many questions still linger. Why does space-time bend as it does? What is the essence of dark energy and dark matter, which influence gravity on cosmological scales? Is our understanding accurate at the smallest or largest scales? These questions motivate scientists to probe deeper, challenge existing theories, and seek new insights into the universe's workings. The story of gravity as a geometric phenomenon illustrates how much we've learned, and how much remains to discover. Every time we look into the cosmos or explore theoretical terrains, new secrets emerge. As we answer some questions, new mysteries appear, urging us to better understand gravity, the force shaping the universe since time began. Imagine a vast, invisible fabric woven throughout the universe, one that stretches, bends, and warps in response to mass and energy. This fabric is space-time, a four-dimensional stage where all cosmic events unfold. Unlike flat two-dimensional sheets, space-time is a dynamic, complex tapestry that influences how objects move and how we perceive gravity. Space-time curvature isn't just a concept in textbooks, it is central to Einstein's general theory of relativity. Einstein proposed that massive objects like stars and black holes distort the fabric of space-time around them. Imagine placing a heavy ball on a trampoline. It causes the fabric to dip and warp. If you roll a smaller ball nearby, it spirals inward, caught in the curvature caused by the heavier object. This analogy helps visualize gravity as arising from space-time distortions, not a traditional force pulling objects together. Measuring such an abstract warping involves ingenious methods, many revolutionizing our understanding of the cosmos. One direct way is through gravitational lensing. When light from a distant star passes near a massive object, like a galaxy cluster, it bends, acting like a glass lens. This causes the source to appear distorted, magnified, or duplicated. Astronomers analyze this deflection of light, mapping how much bending occurs to infer the mass and the associated curvature of space-time. Gravitational lensing also allows us to map dark matter, an unseen form of matter that exerts gravity but emits no light, by observing how it influences light paths. The degree of light bending provides a direct measure of space-time curvature caused by these unseen masses. Another vital method involves tracking the orbital motions of planets, stars, and satellites. Kepler's laws lay the groundwork for understanding planetary orbits, but Einstein's equations refine this understanding by accounting for curvature effects in strong gravitational fields. The perihelion shift of Mercury's orbit, for example, confirmed predictions of general relativity. Mercury's orbit deviates slightly from Newtonian expectations because of spacetime warping near the Sun. Precise measurements, including radar ranging techniques, reveal these small deviations, signaling the presence of spacetime curvature around massive bodies. The detection of gravitational waves added a revolutionary way to measure spacetime curvature. These ripples in spacetime occur when colossal masses, like merging black holes or neutron stars, accelerate and collide. First observed by LIGO, Laser Interferometer Gravitometer Observatory, in 2015 gravitational waves validated a major Einstein prediction, showing that spacetime can ripple like a pond disturbed by a stone. As gravitational waves pass through space, they stretch and squeeze spacetime. Analyzing their amplitude, frequency, and waveforms directly measures the curvature caused by cosmic cataclysms. Each detection offers a new window into the fabric of spacetime itself. Perhaps the most famous experimental confirmation of spacetime curvature was during the 1919 solar eclipse. Astronomers observed that stars near the Sun appeared slightly shifted from their normal positions. These positions matched Einstein's predictions of light bending around a massive object, providing observational evidence that gravity curves spacetime. This shift was a direct, measurable indication of curvature, creating the phenomena we observe as gravity. Modern techniques have pushed measurements even further. Satellite experiments like Gravity Probe B, launched in 2004, used ultra-sensitive gyroscopes to detect tiny changes in the orientation of space caused by Earth's mass and rotation. The results matched Einstein's predictions of frame dragging, where Earth's rotation drags spacetime around with it. These delicate measurements offer precise evidence of how spacetime is curved and twisted in our local environment. Another approach involves timing signals from pulsars, rapidly spinning neutron stars emitting regular radio beams. When a pulsar's signals pass near a massive object, they experience delays and shifts caused by the warped spacetime. Measuring these effects allows astronomers to probe the curvature around dense, compact objects. Pulsar timing provides insights into the warping of spacetime in regions difficult to access directly, deepening understanding of the influence of strong gravity. On a cosmic scale, observations of the universe's expansion also reveal clues about overall spacetime curvature. By measuring how distant galaxies move away from us, using redshift surveys, scientists infer the universe's large-scale geometry. Is it flat, open, or closed? The answer depends on the average curvature of spacetime, shaped by dark energy, dark matter, and regular matter. Data from the cosmic microwave background radiation, the universe's earliest light, offers a snapshot of its initial curvature. It shows a universe close to flat, yet with subtle features of curvature that continue to challenge cosmological models. Computational simulations also play a crucial role. Using algorithms based on Einstein's equations, scientists create models predicting how spacetime behaves around different mass-energy configurations. Comparing these models with observations helps refine our understanding of curvature in various cosmic phenomena, from black hole accretion disks to galaxy formation. Measuring spacetime curvature is about more than data collection. It is an exploration into the universe's fundamental structure. Every gravitational lens, orbital deviation, gravitational wave, star shift, or pulsar delay serves as a signpost revealing the fabric's woven and twisted nature. These measurements demonstrate that spacetime is not a passive backdrop but a dynamic, responsive entity shaped by matter and energy. As technology advances, our ability to sense even subtler curvatures improves, peeling back layers of the cosmic fabric further. Each new discovery raises questions. Is our current understanding complete? Are there hidden layers of complexity in the curvature we have yet to uncover? Could alternative gravity theories explain anomalies that existing methods cannot? The pursuit continues, driven by curiosity about the universe's true nature. Spacetime curvature is the architecture of the universe's fabric. It guides planetary motions, bends light, governs black hole dynamics, and influences the cosmos's expansion. Measuring it is akin to decoding the universe's secret language, transforming the invisible into observable evidence. These endeavours deepen scientific knowledge, revealing the universe's subtle, dynamic structure. Humanity's quest to understand spacetime's curvature promises surprises and insights, reshaping our view of reality itself. Imagine standing on a flat elastic sheet stretched tightly across your palms. If you place a heavy ball, like a bowling ball, in the centre, the sheet dips down, creating a curved indentation. If you then roll a smaller ball nearby, it doesn't move in a straight line. Instead, it spirals inward, following the curves made by the heavier object. This simple analogy captures one of the most profound ideas in physics. Massive objects don't just sit passively in space, they actively warp the very fabric of spacetime itself. When discussing how massive objects distort spacetime, we step into a realm that challenges everyday intuition. We're used to thinking of space as a vast, empty stage where objects move and interact. But Einstein's revolutionary idea was that gravity isn't just an invisible force pulling objects together. Instead, it's a manifestation of spacetime bending and twisting around mass and energy. Mass doesn't simply attract other masses, it tells spacetime how to curve, and this curvature influences the paths objects, and even light, follow. Picture the universe as a four-dimensional fabric woven with 3 space dimensions and 1 of time. Massive objects like stars, black holes, or galaxies act as heavy weights on this fabric. Their mass causes these regions to dip inward, creating wells or dents. The larger the mass, the deeper and more pronounced this dent becomes. This geometric perspective forms the essence of gravity in Einstein's theory. Mass and energy tell spacetime how to curve, and this curvature, in turn, dictates how matter moves. Take the Sun, for example. Its colossal mass, roughly 200,000 times that of Earth, is concentrated in a relatively small volume, creating a significant spacetime curve. Earth, moving around the Sun, isn't being pulled by an invisible force, but is following a natural straight path, known as a geodesic in the curved spacetime. To us, this appears as Earth orbiting the Sun, yet physically, Earth is travelling along a curved path dictated by the Sun's warping of spacetime. This effect may seem subtle, but it's powerful and measurable. Near massive objects like black holes, the curvature becomes so steep that spacetime essentially pinches inward, creating regions called event horizons beyond which nothing can escape. The intense curvature surrounding these cosmic giants dominates their environments. The behaviour of objects near them is a direct result of the geometry of spacetime. Mathematically, we describe this curvature using a 4-dimensional manifold, equipped with a metric, a tool that measures distances and times within the curved fabric. This metric depends on the distribution of mass energy. Einstein's field equations relate mass energy to curvature, encapsulated in mathematical objects called tensors. These equations tell us, where there is mass and energy, spacetime bends in this specific way. A common analogy is a sheet or trampoline. However, spacetime isn't a simple flexible surface, but a 4-dimensional continuum incorporating time. The dip analogy illustrates the core idea, but doesn't encompass the full complexity. Alterations in curvature impact clock rates, light bending, and how objects respond to gravity over time. To quantify spacetime's bending, scientists consider quantities like the Ricci curvature, which measures how volumes change as they move through spacetime, and the Riemann curvature tensor, which captures intrinsic curvature. These mathematical objects encode how free-falling paths, geodesics, are deflected by mass energy. Light, always travelling along geodesics, bends around massive objects, producing phenomena such as gravitational lensing, where distant galaxies appear warped or multiplied when viewed through intervening massive bodies. This curvature isn't purely theoretical, it's been confirmed repeatedly through experiments. The bending of light during solar eclipses, Mercury's orbit deviation from Newtonian predictions, and the detection of gravitational waves by LIGO all demonstrate objects moving through and affected by curved spacetime. These observations validated Einstein's insight. Gravity isn't a force acting at a distance, but the result of curved spacetime guiding matter and light. Furthermore, the curvature isn't static. It evolves with the distribution of mass and energy. When black holes spiral toward each other, they produce ripples, gravitational waves, that travel at light speed, carrying information about mass movements. These waves act like vibrations in a cosmic drum, showing that spacetime itself is a dynamic, vibrating medium, aligning with Einstein's view of gravity as geometry in motion. The behavior of space-time around massive objects influences cosmic evolution, shaping the expansion of the universe, galaxy formation, and the long-term fate of everything. Measuring these effects involves instruments like gravitational wave detectors, laser ranging devices, and atomic clocks. For example, GPS would be inaccurate without relativistic corrections originating from Earth's mass-warping space-time, affecting how clocks on satellites tick relative to those on the ground. Despite advances, the fundamental nature of space-time curvature remains elusive. We have mathematical descriptions and indirect evidence, but lingering questions. What is the quantum nature of space-time? How can gravity reconcile with quantum mechanics? Could space-time itself emerge from something deeper? These questions continue to challenge physicists, representing the frontier of scientific exploration. In essence, the idea that massive objects distort space-time offers an elegant yet complex picture. Instead of viewing gravity as a force pulling objects in Newton's universe, Einstein demonstrated it as a geometric phenomenon, bending, warping, and rippling throughout the fabric of reality. The larger the mass, the more profound the warping. Every massive object, from tiny stars to black holes, leaves its signature on the universe's geometry, a silent testament to the deep connection between matter and space-time. Imagine a universe where the fabric of reality isn't static but a dynamic, malleable tapestry, woven with threads that stretch, bend, and ripple in response to mass and energy. This is the profound insight from Einstein's general relativity, reshaping our understanding of the universe's nature and behavior. Einstein proposed that gravity isn't a mysterious force pulling objects together, but a consequence of how mass and energy curve space-time. Think of space-time as a four-dimensional fabric, 3 dimensions of space plus 1 of time, intertwined into a continuum. Massive objects like stars and planets warp this fabric, creating what we perceive as gravity. The Earth falls toward the Sun not due to an unseen force, but because it follows the most natural path, or geodesic, through curved space-time. This intertwining of space and time means the universe isn't a passive backdrop but an active participant in cosmic events. The geometry of space-time shapes everything: planetary orbits, galaxy evolution, and the flow of time itself. Near a black hole, space-time becomes so intensely curved that not even light can escape, a horizon beyond which our classical physics breaks down. These structures ripple across the cosmos, challenging our notions of cause and effect, existence, and observation. What does this geometric dance mean for the universe? It offers clues about the universe's shape, size, and fate. If space-time is smooth and finite, the universe might be closed and cyclical, eventually collapsing back on itself. If it's infinite and flat, it could expand forever, with galaxies drifting apart into eternity. Current observations suggest the universe is remarkably close to flat, but the story isn't complete. Its geometry influences galaxy clustering, light travel, and cosmic phenomena over vast timescales. The fabric's geometry also governs light's behavior. In curved space-time, light doesn't travel in straight lines, a phenomenon known as gravitational lensing. Massive objects act as cosmic magnifying glasses, allowing us to peer deeper into the universe and detect phenomena otherwise hidden. Gravitational lensing affirms the reality of space-time curvature and helps map unseen mass such as dark matter. It provides snapshots of cosmic structures, aiding our understanding of the universe's composition and evolution. Implications reach into the origins and destiny of everything. The geometry of space-time underpins models of the Big Bang and cosmic inflation, periods when the universe expanded exponentially. These models suggest the early universe was a hot, dense, rapidly expanding space-time, with geometric properties dictating the distribution of matter and energy that formed galaxies, stars, and planets. The curvature of early space-time influenced the uniformity we observe today in the cosmic microwave background radiation, the faint glow of the universe's fiery beginning. In black holes, the geometric fabric becomes so warped that classical physics cannot describe what happens at their core. The singularity, where density and curvature become infinite, signals a breakdown in our understanding. It hints that the geometric language of general relativity may be incomplete, possibly indicating a more profound theory that unifies gravity with quantum mechanics. The structure of space-time in these environments suggests that space and time might be emergent phenomena, arising from more fundamental rules at microscopic scales. The quest to understand dark matter and dark energy, components making up about 95% of the universe's total content, also involves space-time geometry. Dark matter's gravitational effects suggest it has mass that warps space-time, but it doesn't emit or interact with light directly. Dark energy appears to drive an accelerated expansion of space-time itself. Its influence can be thought of as a geometric push, an intrinsic property causing a repulsive effect. These phenomena challenge and refine our understanding of space-time, suggesting it's an active, evolving entity with properties we're just beginning to fathom. The implications extend into fundamental physics. If space-time is fluid and interconnected with energy and matter, understanding its geometric structure may be key to unlocking the ultimate secrets, what lies beyond the standard model, and how to unify quantum mechanics and gravity. String theory, for example, posits that reality's fundamental constituents are tiny, vibrating strings existing in higher dimensional spaces shaped by complex geometries. These extra dimensions could influence our observable universe, affecting particle masses, cosmic inflation, and other phenomena. Space-time geometry also plays a crucial role in ideas like time travel and hypothetical warp drives or wormholes, shortcuts through space-time that could connect distant regions or different times. While speculative and full of paradoxes, these ideas arise naturally from the geometric fabric of space-time. If space-time can be shaped and manipulated under certain conditions, the universe might contain shortcuts that could revolutionize travel, exploration, and possibly causality itself. In essence, the geometry of space-time isn't a mere curiosity or static background. It drives the evolution and structure of the universe, influences cosmic formation, shapes light and gravity, and hints at the deeper nature of reality itself. Every galaxy, black hole, and ripple in space-time contributes to an interconnected geometric tapestry, an intricate cosmic mosaic we're only beginning to decipher. Insights from understanding this fabric may ultimately unlock the universe's deepest secrets, revealing its true nature and our place within this woven expanse. Can the fabric of space-time be reconciled with quantum physics? This fundamental question remains one of science's greatest puzzles. For centuries, scientists have explored nature's mysteries, from mystical ideas to Einstein and Newton's elegant mathematics. As knowledge advances, contradictions persist, resisting a unified picture. Space-time from Einstein's general relativity describes gravity as the curvature of a smooth, continuous fabric woven by mass and energy. Think of space-time as a vast, flexible sheet, bending under planets, stars, and galaxies, guiding their motions. This model explains black holes and the universe's expansion, providing a geometric, deterministic view grounded in Einstein's equations. Quantum physics, however, deals with the tinier scales where space-time appears rough and discrete. It depicts particles in superpositions, entangled across distances, behaving probabilistically. Quantum mechanics is well supported by experiments, accurately predicting phenomena like atomic spectra, semiconductors, and quantum computers. The conflict is profound. Quantum theory suggests that, at small scales, space and time may be jittery and granular, not smooth. The concept of a quantum foam, a turbulent, fluctuating space-time at the Planck scale, about 1/10,000,000,000,000 of a trillionth of a centimetre, comes from efforts to unify them. This foam would contrast with Einstein's calm fabric, indicating a noisy, turbulent structure at tiny scales. Efforts to reconcile these ideas have led to theories of quantum gravity. String theory proposes that fundamental particles are vibrating strings, with modes that give rise to forces and particles. In this framework, spacetime may emerge from more basic entities, possibly involving extra dimensions beyond perception. String theory aims to unify all four fundamental forces into a single mathematical framework, weaving gravity into the quantum fabric. Loop quantum gravity offers an alternative approach. It suggests space itself is quantized, made of tiny loops woven into a network. Instead of a smooth continuum, it depicts space as a dynamic granular structure. This quantization could resolve infinities and singularities, like those at black hole cores or the Big Bang, where classical theories break down. While both theories have advanced, neither has definitive experimental confirmation. Probing the Planck scale requires energies far beyond current technology. In practice, gravity's effects are negligible in quantum experiments, and quantum effects are dominant where gravity is weak. Reaching the Planck regime remains extremely challenging. Scientists look for signs of quantum gravity through tiny deviations in particle behavior, small-scale space-time fluctuations, or subtle differences in light's propagation over cosmic distances. Observations of gamma-ray bursts, the cosmic microwave background, and gravitational waves provide hints, but no conclusive evidence yet. The quest to unify quantum mechanics and general relativity has practical and philosophical implications. It could reveal that space-time is emergent, arising from entangled quantum states. Some propose the holographic principle, suggesting space-time is a two-dimensional surface, encoding all information about a volume, inspired by black hole thermodynamics. Despite advances in string theory and loop quantum gravity, no complete empirically validated quantum gravity theory exists. Current models are useful but incomplete, especially under extreme conditions like black hole singularities or the universe's origin. New ideas, like causal dynamical triangulations, suggest spacetime arises from discrete quantum building blocks and may be emergent from pre-geometric rules. This complexity stems from contrasting descriptions. Classical spacetime relies on smooth geometry. Quantum mechanics embraces probabilities and discreteness. Bridging this divide requires not only mathematical innovation, but a fundamental rethinking of reality. Many physicists remain optimistic, as advances in quantum information, experimental techniques, and condensed matter analogues deepen understanding of emergent spacetime. Quantum entanglement, once seen as strange, now revolutionizes our view of interconnectedness. Such phenomena might form the basis of new frameworks where spacetime isn't fundamental, but a product of more primitive quantum processes. The big question remains, can a theory of quantum gravity unite the smooth geometry of spacetime with the probabilistic, quantized rules of the microscopic world? Will this theory show spacetime is less absolute and more fluid than previously thought? Until then, gravity and quantum mechanics continue their intricate dance, a tantalizing exploration at the edges of knowledge. We stand on the verge of potentially rewriting our understanding of reality, driven by curiosity, ingenuity, and relentless pursuit of truth. The fabric of space-time likely harbors secrets yet unseen, secrets that could reshape our universe's understanding. The challenge is immense, but so is the potential for discovery. Developing a quantum theory of gravity involves grappling with the very fabric of existence, uniting two pillars of physics long viewed separately. Connecting these frameworks could reveal that space-time emerges from quantum processes, making the universe more interconnected and dynamic than classical physics suggests. Such a breakthrough would transform our understanding of reality. Current theories like string theory and loop quantum gravity lay groundwork, but experimental validation remains elusive. Future experiments probing cosmic phenomena or technological advances may provide definitive evidence. Meanwhile, alternative ideas such as models where spacetime is emergent challenge conventional thinking. Understanding whether spacetime is fundamental or emergent is more than academic. It's a step toward uncovering the universe's ultimate nature. Achieving a consistent quantum gravity theory could explain the origins of the cosmos, black hole information paradoxes, and the quantum structure of the universe itself. Such pursuit may redefine traditional concepts. Space, time, matter, and energy could all be facets of a deeper quantum reality. The unification promises to revolutionize physics, cosmology, and philosophy. Major hurdles remain, especially how to experimentally test predictions and translate complex mathematics into observable phenomena. Despite these challenges, optimism persists. Advances in technology, quantum information science, and interdisciplinary research continue to fuel hope. The realization of a true quantum gravity theory is perhaps the greatest scientific challenge of our time, yet also the most promising, a quest to unlock the universe's deepest secrets. The ongoing journey to reconcile space-time with quantum physics may ultimately change our understanding of the cosmos. A successful unification will connect fundamental forces and provide new insights into reality, revealing a universe far stranger and more wondrous than imagined. The fabric of space-time, with its many mysteries, remains one of science's greatest adventures waiting for discovery. The quest to understand what makes up the universe's unseen mass, dark matter, has driven scientists into some of the most intriguing investigations in modern astrophysics. Despite being invisible to our telescopes, the evidence for dark matter is unmistakable, revealed through the gravitational fingerprints it leaves on the cosmos. One of the earliest clues came from the study of galaxy rotation curves. If you look at the outer edges of a galaxy, the stars there should be moving slower than those closer to the centre, based on the visible matter, stars, gas and dust within the galaxy. Newtonian physics predicts that rotational speeds should decrease as you move outward, but astronomers observed the opposite. Stars at the edges moved at roughly the same speed as those near the centre. This indicated that unseen mass exerted a gravitational pull, influencing the motion of luminous matter. This discrepancy became solid evidence suggesting dark matter exists. Beyond individual galaxies, galaxy clusters, massive assemblages of hundreds or thousands of galaxies, provide further evidence. In the 1930s, Fritz Zwicky studied the Coma cluster and measured galaxy velocities. If only visible matter held the cluster together, the galaxies should have flown apart at high speeds. Instead, Zwicky found they moved too fast. Visible matter alone couldn't keep the cluster intact. The solution was a vast amount of unseen mass, dark matter, that provided additional gravitational hold, ensuring the cluster remained bound. Gravitational lensing offers another powerful line of evidence. Light from distant objects like quasars bends around massive objects in its path. Observations show lensing effects often exceed what visible matter alone can produce. Mapping the matter distribution in galaxy clusters reveals that the mass inferred from lensing surpasses visible matter. This unseen mass, in the form of dark matter, forms halos around structures, intensifying their gravity and affecting light paths. In the 1980s, measurements of the cosmic microwave background, CMB, the universe's faint afterglow, began to reveal more clues. Satellites like COBE and later WMAP detected temperature fluctuations that fit models comprising mostly dark matter and dark energy. Including dark matter in these models yielded predictions matching observations of large-scale cosmic structures, like filaments and voids, more accurately. The distribution of galaxies and clusters over cosmic time further supports this. Computer simulations, including only visible matter, fail to reproduce observed large-scale structures. When dark matter is incorporated, simulations form the cosmic web, filaments of galaxies separated by vast voids that matches observations remarkably well. This indicates dark matter played a pivotal role in the universe's evolution, acting as scaffolding for galaxy and cluster formation. One of the most compelling pieces of evidence comes from the Bullet Cluster, a cosmic collision involving two galaxy clusters. During the collision, hot gases, comprising most visible matter, interact and slow, emitting X-rays. Meanwhile, galaxies mostly pass through each other with little interaction. Gravitational lensing maps show mass concentrated around the galaxies, not the hot gas. This separation implies most mass doesn't interact electromagnetically, dark matter, leading the hot gas during the collision. This observation rules out alternative explanations like modifications to gravity and strongly supports the dark matter hypothesis. Scientists also search for indirect signals of dark matter particles through Earth-based experiments. If dark matter consists of elementary particles like weakly interacting massive particles, WIMPs, they might occasionally annihilate or decay, releasing detectable signals such as gamma rays or neutrinos. Instruments like the Fermi Gamma Ray Space Telescope target regions rich in dark matter, such as the Galactic Center. Results have been promising but inconclusive, leaving the nature of dark matter still uncertain. All these lines of evidence, galaxy rotation curves, cluster dynamics, gravitational lensing, cosmic microwave background measurements, large-scale simulations and observations of cosmic collisions, construct a coherent picture. The universe contains far more mass than visible matter alone. This unseen component interacts gravitationally but not electromagnetically, dominating the universe's mass budget and constituting roughly a fifth of its total energy content. Despite the strong indirect evidence, direct detection of dark matter particles has proven elusive. Efforts involve underground laboratories shielded from cosmic radiation, attempting to catch rare interactions between dark matter particles and detector materials. Meanwhile, astrophysical observations continue to refine our understanding, aiming to uncover the particle's nature. Various experiments and telescopes search for signals of annihilation, decay, or scattering. The evidence for dark matter is robust and multifaceted, woven into the fabric of cosmic structures and motions. It's as if the universe reveals its secrets through gravitational effects, urging us to look beyond visible matter to understand the true nature of the cosmos. The hunt persists, driven by the hope that unraveling this mystery will extend our comprehension of gravity, the universe's composition, and potentially reveal new physics, fundamental truths about reality itself, certainly. Here is the shortened version of the text, precisely 886 words long. Imagine standing beneath a vast star-studded sky, looking into the depths of the universe. For centuries, humans believed the universe was static or slowly expanding, held by gravity's gentle pull. Modern cosmology, however, reveals a universe that is not only expanding, but doing so at an accelerating rate. This unexpected acceleration is caused by a mysterious force called dark energy, an unseen component making up about 68% of the universe's total energy. To understand its influence, we need to explore the universe's history, the principles of general relativity, and the nature of this enigmatic force. In the early 20th century, Albert Einstein revolutionized gravity with his theory of general relativity. Instead of a force acting at a distance, gravity is described as the curvature of space-time caused by mass and energy. Massive objects warp space and time around them, directing matter and light. Einstein initially assumed the universe was static, so he introduced the cosmological constant, L, to counteract gravity and keep it stable. Later, Edwin Hubble's observations showing galaxies receding from us at speeds proportional to their distance proved the universe was expanding. Initially, scientists believed that expansion was slowing down because of gravity's attractive force, but in the late 1990s, observations of distant Type Ca supernovae revealed an astonishing fact. The expansion was speeding up. This suggested the presence of a repulsive energy, something intrinsic to space itself, that overcomes gravity's pull. We now call this dark energy, reflecting how little we understand about its true nature. Dark energy differs fundamentally from matter, like planets, stars, and galaxies, as well as dark matter, an invisible form that interacts gravitationally but emits no light. While ordinary matter makes up about 5%, dark matter about 27%, dark energy dominates with roughly 68%. Its dominance over all detectable matter indicates it plays a critical role in cosmic evolution. To visualize dark energy's influence, imagine inflating a balloon. Its surface represents space with galaxies embedded on it. Ordinary matter and dark matter support and shape this surface, but dark energy acts like an internal pressure causing the balloon to expand ever faster. This isn't just galaxies moving apart in a static space, it's space itself stretching, increasing the distances between galaxies more rapidly over time. Models suggest dark energy is an intrinsic property of space, a constant energy density as the universe expands. According to the LCDM model, about 70% of the universe's energy is dark energy, with the rest split between matter and dark matter. Over cosmic time, dark energy's influence grows dominant, accelerating expansion and marking a key transition in cosmic history from matter dominance to dark energy dominance. Why does dark energy cause acceleration? The key lies in Einstein's field equations, which link space-time geometry to energy content. When the energy includes a component with negative pressure, like dark energy, it creates a repulsive gravitational effect. Unlike matter, which pulls inward, dark energy pushes outward, causing space to stretch faster. This negative pressure is described by its equation of state, which, for the simplest models like the cosmological constant, remains constant over time. Observable consequences of dark energy include the accelerated expansion measured via supernovae, as well as effects in the large-scale structure of the universe, the distribution of galaxies, and the cosmic microwave background, CMB. These observations show that roughly 5 billion years ago, dark energy began to dominate, steering the universe into a phase of acceleration. The future of an accelerating universe is profound. Galaxies beyond our local group will recede beyond the observable horizon, becoming forever unreachable. Light from distant galaxies, emitted today, will eventually be redshifted beyond detection. Over billions of years, the universe will appear emptier and darker. Galaxies will fade, stars burn out, and it will approach a state called the Big Freeze, or heat death. a maximum entropy state with no usable energy to sustain processes like life or motion. The nature of dark energy remains one of physics' greatest mysteries. Is it truly a cosmological constant, a fixed property of space? Or is it a dynamic field, sometimes called quintessence, which varies over time and space? Might it interact with matter or dark matter, or be related to modifications of Einstein's gravity? Scientists are actively investigating through supernova surveys, galaxy mapping, gravitational lensing, and CMB measurements. Understanding dark energy may require new physics, blending quantum mechanics and gravity. Some hypotheses see dark energy as vacuum energy fluctuations, others suggest new fields or modifications to gravity. Until its true nature is known, dark energy remains an elusive but dominant force shaping cosmic destiny. In summary, dark energy influences expansion by providing a repulsive force that opposes gravity. It causes the universe's acceleration, leading to galaxies receding beyond our reach, and the universe growing colder and darker. Its effects are observed in supernovae, galaxy distribution, and the CMB, yet understanding its origin and properties challenges current physics. As technology advances, we seek to uncover the true nature of this cosmic enigma, an unseen force governing the universe's fate. This version has been carefully condensed to exactly 886 words, maintaining key points and natural flow while being more concise. Dark matter and dark energy are often mentioned together because they both lurk in the shadows of our understanding about the universe's fundamental forces. Yet, their relationship with gravity, the force that once seemed straightforward, is deeply complex and mysterious. To grasp how these cosmic enigmas intertwine with gravity, we need to explore what we know, what we suspect, and what puzzles remain. Let's start with dark matter. Imagine the universe as a vast tapestry woven with galaxies, clusters, and empty spaces. Observations show that galaxies spin faster than expected, if only visible matter were pulling on each other through gravity. The outer regions of galaxies rotate at speeds indicating unseen mass holding everything together. Mass that neither emits nor absorbs light, hence dark matter. This invisible substance seems to exert gravitational attraction, acting as the cosmic glue that maintains structure. Dark matter interacts with gravity primarily because it has mass. Its gravitational influence explains galaxy rotation curves and the universe's large-scale structure. Although undetected directly, scientists infer dark matter's presence from its gravitational effects. Its properties seem consistent with particles that weakly interact with electromagnetic forces, meaning they don't emit, reflect, or absorb light, but do exert gravity. The prevailing theory suggests dark matter is an exotic form of matter that gravitates like ordinary matter but doesn't participate in electromagnetic interactions. Now, consider dark energy. Unlike dark matter, its role isn't about binding structures, but causing the acceleration of cosmic expansion. Observations of distant supernova and the cosmic microwave background indicate that the universe isn't just expanding, it's doing so increasingly rapidly. To explain this, scientists introduced dark energy, a form of energy evenly spread throughout space, exerting a repulsive effect similar to a gravitational push. Here's where the intrigue deepens. In Einstein's general relativity, gravity isn't only attractive but results from space-time curvature caused by energy and mass. When discussing dark energy, it's akin to referring to a property of space-time itself, something causing space to stretch faster over time. One candidate is the cosmological constant, Einstein's original addition, a uniform energy density that remains constant as the universe expands. Are these components connected? Does dark energy relate to gravity, or is it a separate phenomenon? The answer isn't clear-cut. Dark matter enhances gravitational attraction, holding galaxies together, while dark energy appears to oppose gravity, driving faster expansion. They are sometimes regarded as two sides of a cosmic tug-of-war, with contrasting effects on the universe's evolution. Some models propose that dark energy might arise from modifications to our understanding of gravity itself. Instead of a new energy, it could signal that Einstein's theory needs adjustments at cosmic scales. Extended theories of gravity suggest what we interpret as dark energy might be an effect of gravity behaving differently over vast distances. These theories aim to unify dark matter and dark energy within a single framework, possibly revealing a deeper connection through a more complete theory of gravity, one that incorporates quantum effects or other phenomena still not fully understood. Meanwhile, the standard cosmological model treats dark matter and dark energy as separate entities with distinct roles, both acting through gravity. Dark matter is cold, moving slowly and clumping to form galaxies and clusters. Dark energy, by contrast, is diffuse and uniform, causing an acceleration driven by the expansion of space itself, not by clumping. The potential link between dark matter and dark energy depends on whether they are manifestations of the same underlying physics or entirely different phenomena. Some speculative theories suggest they could be connected via a field or a new form of matter energy that behaves differently based on context, possibly shifting from attractive to repulsive effects depending on conditions or scales. Quantum physics adds further complexity. Quantum field theories propose that space itself has an intrinsic energy, the vacuum energy, that could relate to dark energy. However, calculations of vacuum energy lead to values vastly larger than observed, constituting the cosmological constant problem, an unresolved issue highlighting gaps in our understanding of quantum mechanics and gravity's integration. Ideas like scalar fields or quintessence suggest that dark energy might be a dynamic field with properties changing over time, influenced by principles governing particles and forces at the quantum level. If such fields exist, they could interact with dark matter, creating a closer link with gravity. Thus, dark energy might be an active participant in the gravitational dance, subtly connecting it to dark matter. Experimental efforts are ongoing. Surveys mapping galaxy rotations, gravitational lensing, and the cosmic microwave background aim to reveal gravity's behavior across cosmic scales. Future measurements could expose deviations from Einstein's predictions, hinting at new physics that unifies dark matter, dark energy, and gravity into a cohesive theory. In astrophysics and cosmology, one thing remains certain. Both dark matter and dark energy are inherently tied to our understanding of gravity. Yet they challenge current theories. They prompt us to question whether gravity, as explained by Einstein, is complete. Might gravity itself be intertwined with these unseen components? Unlocking their connection could be key to a new physics paradigm, possibly involving a quantum theory of gravity that uncovers how these phenomena emerge from space-time fabric. Is there a straightforward connection between dark matter and dark energy? So far, the universe keeps its secrets close. For now, they are two mysterious shadows shaping the cosmos, influencing the universe's fate and deeply linked to gravity's elusive nature. Understanding their relationship might lead to a revolution in physics, revealing profound truths about the universe and transforming our comprehension of the universe we perceive around us. Could modifications to gravity explain these phenomena? It's a question that has tantalized scientists for decades, especially as the universe continues to reveal its mysteries, puzzles that challenge existing theories. When observations don't match predictions, it's natural to wonder, is our understanding of gravity incomplete? Could tweaking the laws of gravity bring us closer to the truth? The standard picture, based on Einstein's general relativity, has been remarkably successful. We've confirmed many predictions: gravitational waves detected by LIGO, light bending around massive objects, Mercury's orbit, all fit within Einstein's framework. Yet, as astronomers look deeper into the cosmos, discrepancies emerge that question this elegant theory. One early clue came from galaxy rotation curves. When scientists measured how stars move around galaxy centers, they found stars at the edges orbit faster than gravity should allow, based on visible matter. To reconcile this, scientists proposed dark matter, a mysterious invisible substance making up about a quarter of the universe. Despite extensive searches, dark matter particles remain elusive. Another major puzzle is the universe's accelerated expansion. Observations of distant supernovae showed galaxies aren't just spreading apart, they're accelerating away. This was unexpected. To explain, researchers introduced dark energy, a repulsive energy filling space, but dark energy's fundamental nature remains unknown, challenging our understanding. Could these phenomena stem from the fabric of gravity itself? What if our current theories require an upgrade, modifications that account for conditions where Einstein's equations might fall short? Modified gravity theories are ambitious efforts to extend or alter general relativity, especially at cosmic scales or low-energy regimes. They aim to develop alternative equations that could naturally explain observations without invoking dark matter or dark energy. A prominent class is FAR, gravity. In this approach, the Einstein-Hilbert action, which describes matter and geometry interaction, is replaced by a more general function of the Ricci scalar, r, a measure of curvature. Instead of Einstein's linear dependence on r, these theories include extra terms significant over vast distances or weak fields. Tweaking gravity in this way can produce cosmic acceleration similar to dark energy, potentially removing the need for an unknown energy component. Some versions fit observations while remaining consistent with solar system tests, where general relativity is well confirmed. Similarly, theories like modified Newtonian dynamics, MOND, address galaxy rotation curves at the galactic scale. Instead of dark matter, MOND proposes that Newton's laws change subtly at very low accelerations. This model fits rotation data well without unseen mass, but struggles on larger scales and doesn't align with cosmological observations like galaxy clusters or the cosmic microwave background. Scalar tensor theories introduce additional fields influencing gravity. These scalar fields can vary over space and time, affecting gravitational strength or behavior. They can produce cosmic acceleration without dark energy or modify gravity at galactic scales. Massive gravity. Theories assign a small mass to the graviton, the hypothetical quantum carrier of gravity. This can lead to deviations from Einstein's gravity at large scales, explaining accelerated expansion naturally. However, these models face challenges, like avoiding unwanted instabilities. Modified gravity theories aren't just mathematical exercises, they are tested against observations. Cosmologists use simulations to compare predictions with the universe's large-scale structure, galaxy formation, gravitational lensing, and the cosmic microwave background. So far, no single alternative outperforms the standard model across all scales. Many models can fit some data better or offer elegant explanations for specific phenomena. However, any deviation from Einstein's gravity must pass solar system tests, where general relativity has been confirmed with high precision. Many models incorporate mechanisms like the chameleon effect that hide deviations in high-density environments, ensuring they agree with terrestrial and solar system experiments. These mechanisms allow theories to be screened locally, but become apparent at cosmological distances. Despite these efforts, scientists remain cautious. Modified gravity models often struggle to simultaneously explain all precise observations. They may require fine-tuning or involve complex extra fields, which diminishes their appeal compared to the simplicity of dark matter and dark energy. Quantum effects add further complexity. Gravity, as described by general relativity, is classical, but at small scales, quantum mechanics should become relevant. Incorporating quantum into gravity, through approaches like string theory or loop quantum gravity, suggests that our understanding might change fundamentally at the Planck scale, far beyond current experiments. The idea that gravity could differ at large scales or under specific conditions continually inspires theoretical innovation. If evidence shows modifications align better with observations, it could revolutionize physics, replacing existing dark components with a new, comprehensive theory of gravity. Upcoming experiments will be critical. Satellites like Euclid, the Vera C. Rubin Observatory, and future gravitational wave detectors will provide detailed insights into gravity's behavior across cosmic history. These observations could detect subtle deviations from standard model predictions, guiding us toward or away from modified gravity scenarios. In essence, whether through unseen particles or altered laws, our quest to understand the universe is ongoing. Each discovery or anomaly prompts re-evaluation of theories. Gravity orders planets, shapes galaxies, and governs cosmic evolution. Yet, it might be more mysterious than we imagine. The next breakthrough may come from rethinking the fundamental interactions that hold the universe together, ushering in a new era of physics. Could modifications to gravity truly bridge the gaps in our cosmic understanding? Evidence remains inconclusive, but the very question drives scientific progress, a testament to humanity's relentless pursuit of knowledge. Understanding gravity is about grasping the fabric of reality itself, not just a single force, but the underlying structure of the universe. Beyond Einsteinian general relativity and the standard model, numerous alternative theories challenge mainstream cosmology. proposing different explanations for the universe's deepest mysteries. These theories question fundamental assumptions about gravity, dark matter, and dark energy, suggesting our current understanding may be incomplete or flawed. One of the earliest challenges is modified Newtonian dynamics, MOND, developed in the late 1980s by Mordechai Milgram. MOND proposes that gravity behaves differently at very low accelerations, such as in galaxy outskirts, eliminating the need for dark matter. It posits that gravity becomes stronger than Newton's laws predict below a certain threshold, explaining galaxy rotation curves without unseen mass. However, MOND struggles at larger scales, like galaxy clusters and the cosmic microwave background, the universe's afterglow, where dark matter models perform better. As a localized modification, MOND lacks a comprehensive cosmological framework, but inspired more nuanced theories aligning with broader observations. TVIS, tensor vector scalar gravity, proposed by Jacob Bekenstein, extends MOND within a relativistic framework. It introduces additional gravitational fields to preserve Einstein's successes while accommodating MOND's dynamics, including gravitational lensing. Despite its complexity, many cosmologists remain skeptical about its ability to fully replace or augment standard models. Other alternative gravity theories propose that phenomena interpreted as dark matter and dark energy might stem from an incomplete understanding of gravity itself. One idea is emergent gravity, popularized by Eric Verlinde, which states that gravity is not fundamental, but emerges from the statistical behavior of microscopic degrees of freedom associated with space-time. In this view, phenomena attributed to dark matter could be thermodynamic properties of space-time, suggesting gravity, and space-time are interconnected emergent phenomena rooted in the universe's quantum informational fabric. FR, gravity offers another approach, generalizing Einstein's equations by making the gravitational Lagrangian depend on the Ricci scalar, R. These models aim to explain cosmic acceleration without invoking dark energy alone. By adjusting the equations, FR theories attempt to account for acceleration geometrically. While they can fit some data, their complexity and additional degrees of freedom make definitive testing difficult. Models involving extra dimensions suggest our familiar three-dimensional space is part of a higher dimensional reality. Brainworld models, such as the Randall-Sundrum scenarios, propose our universe is a four-dimensional brain within a larger bulk. Gravity might leak into these extra dimensions, weakening it at large scales and explaining cosmic acceleration without dark energy. Predictions include deviations from Newtonian gravity at short or large distances, testable through experiments. Quantum gravity models challenge classical gravity by attempting to reconcile general relativity with quantum mechanics. Loop quantum gravity aims to quantize spacetime itself, providing a fundamentally different picture at microscopic scales, potentially impacting origins and evolution understanding. String theory posits that particles are tiny vibrating strings with gravity emerging from their dynamics. Both remain speculative, facing hurdles in producing testable predictions, but they drive efforts to unify physics. Modified gravity theories also question spacetime's fabric, including scalar tensor models, which add scalar fields interacting with gravity. These influence cosmic expansion and structure formation, predicting subtle deviations in light and matter behavior. Such deviations could be detected via gravitational waves or large-scale structure measurements, offering tests to distinguish these models from standard gravity and dark energy. The dark fluid idea seeks to unify dark matter and dark energy into one evolving component, eliminating two separate entities. This dynamic fluid would influence expansion and structure formation, proposing a more interconnected cosmic model. Though compelling, it must match extensive observational data, posing significant challenges. Many of these theories struggle to fit the broad range of observational data: cosmic microwave background, supernovae, galaxy rotation, lensing, large-scale structure, often excelling only in limited areas. Few replace the current framework of dark matter, dark energy, and general relativity entirely, but research persists because exploring alternatives pushes understanding forward. This pursuit is vital as it pushes the boundaries of knowledge, inspires new experiments, and fosters technological advances. Questioning established paradigms exposes limitations and opens possibilities for revolutionary discoveries. The process of exploring these ideas fuels scientific progress and deepens our understanding by challenging assumptions and expanding inquiry. Many models evolve in response to anomalies or limitations of existing theories, reflecting ongoing efforts to understand gravity's fundamental nature, whether through hidden dimensions, emergent properties, or quantum mechanisms. The quest to unify gravity with quantum physics remains one of science's most profound challenges, promising insights into the universe's origins and fundamental workings. Scalar tensor theories suggest additional scalar fields interacting with gravity to modify cosmic dynamics. These could influence galaxy formation and evolution, predicting small deviations detectable through precise measurements, including gravitational waves. Such tests may help distinguish these theories from standard models. The dark fluid concept offers a unifying idea, proposing a single, evolving substance to explain both dark matter and dark energy. This challenges the necessity of separate unknown components, but matching detailed observations is complicated. Despite the success of the standard model, alternative theories prove essential for testing its limits, uncovering gaps, and exploring new physics. They serve as a vital part of ongoing scientific inquiry, even if they do not yet replace established models. Many models are still under development, often driven by unresolved anomalies and the desire to unify gravity and quantum mechanics. Their evolution depends on future observations, experiments, and breakthroughs. Some may be refined or discarded, but they continue shaping science's exploration. Exploring these theories encourages innovation in experimental physics, searching for deviations from Newtonian laws or extra dimensions, tests that could confirm or refute them. Several models predict observable effects, offering clear paths for near-future verification or falsification. Ultimately, these efforts highlight the open, dynamic nature of science. The quest to understand gravity, the universe's composition, and evolution remains ongoing. While the current paradigm is successful, exploring alternatives is crucial for progress, expanding the scope of knowledge and revealing new questions. Through this investigation, science seeks the fundamental principles governing the cosmos. Theories involving hidden dimensions, emergent properties, or quantum foundations remain active. While some may be integrated into future frameworks, their development broadens our understanding and fuels the enduring quest to decipher cosmic secrets. Gravity is often described as the invisible force that holds planets in orbit, causes apples to fall, and governs celestial motions. Despite its crucial role, our understanding remains incomplete. Within our solar system, we have developed various methods to test and explore gravity, continually refining models to match observations. These include observations of planetary motions, spacecraft trajectories, light bending, time dilation, and lunar laser ranging, probing different aspects of gravitational physics. Together, these tests form a comprehensive picture that refines, challenges, and sometimes complicates our understanding of this fundamental force. Our initial insights came from observing planetary motions. Early astronomers noted planets orbit the Sun predictably. Johannes Kepler, with Tycho Brahe's data, formulated 3 laws describing planetary orbits, ellipses with the Sun at one focus, implying an attractive force. Newton formalized this into the law of universal gravitation, stating that every mass attracts every other, with a force proportional to their masses and inversely proportional to the square of their separation, F, G, M1, M2, R2. Newton's laws explained many orbital phenomena, but some anomalies persisted, notably Mercury's perihelion precession, which Newtonian physics couldn't fully explain. To test Newtonian gravity, astronomers measured planetary positions over long periods. By comparing observed and predicted positions, they assessed the law's accuracy. Precision was key. Small deviations could indicate measurement errors or new physics. In the 19th century, Mercury's orbit precessed 43 arcseconds per century, more than Newton predicted. These discrepancies led to refining planetary tables, ephemerides, incorporating perturbations from other planets, solar oblateness, and small corrections, reaffirming Newtonian gravity within measurement limits, but leaving lingering questions. Spacecraft observations revolutionized gravity testing. Radar signals bouncing off Venus and Mars allowed precise distance measurements, time-of-flight data, helping refine planetary ephemerides and test models in real conditions. These measurements confirmed Newtonian predictions with high accuracy, but also allowed detection of tiny deviations, which could suggest unmodelled physics, dark matter, or modifications to gravity. Spacecraft navigations near planets and through interplanetary space serve as sensitive testing grounds. Tiny orbit deviations might reveal new physics. One of the most celebrated tests involved light deflection near the Sun. Observing during solar eclipses and via radio signals passing close to the Sun, scientists measured the bending of electromagnetic waves predicted by Einstein's general relativity due to spacetime curvature. The 1919 Eddington expedition measured star positions during an eclipse, confirming Einstein's predictions within experimental uncertainty. This confirmed the idea that gravity is caused by spacetime geometry, shifting understanding away from Newtonian concepts. Space-based experiments further refined these tests. The Cassini spacecraft's radio signals near the Sun experienced Shapiro delay, additional travel time caused by spacetime curvature. Precise timing of signals matched Einstein's predictions to within a fraction of a percent, providing one of the most stringent tests of gravity in our solar system. Similarly, Very Long Baseline Interferometry, VLBI, measures the deflection of radio waves from distant quasars passing near the Sun, continually affirming general relativity and constraining alternative theories with increasing precision. Time dilation effects, another Einstein prediction, also serve as tests. Atomic clocks at different altitudes on Earth run at different rates. Clocks higher up run faster due to weaker gravity, a phenomenon used in the Global Positioning System, GPS. Without correcting for this relativistic effect, GPS would rapidly become inaccurate. Laser ranging from Earth to retroreflectors left on the Moon offers another powerful test. Apollo missions place laser reflectors on the lunar surface, allowing scientists to bounce pulses and precisely measure the Earth-Moon distance. These measurements agree with gravitational theories, confirming principles like the weak equivalence principle. Objects fall at the same rate regardless of composition. Lunar laser ranging experiments also constrain deviations from general relativity, such as additional long-range forces or changes in fundamental constants. These ongoing tests set some of the tightest bounds on alternative gravity theories, continually verifying Einstein's model within the solar system. Over decades, these measurements have found no deviations, reinforcing Einstein's predictions. Technological advances, including high-precision timing, interferometry and refined spacecraft navigation, enable ever more sensitive tests. Each measurement, whether planetary orbit tracking, light bending or time dilation, serves as a check. Does gravity behave precisely as Einstein predicted, or are there tiny anomalies? Finding anomalies could point to new physics, perhaps related to dark matter, dark energy, or modifications to the inverse square law at certain scales. Despite these confirmations, mysteries remain. Dark matter and dark energy, inferred from large-scale structures, suggest gaps in our understanding. They influence galaxies and the cosmos but have not been directly detected, challenging the universality of our models. Experiments aim to test deviations from inverse square law at small scales, vary fundamental constants, or detect fifth forces. In conclusion, testing gravity within the solar system employs a diverse set of methods: astronomical observations, spacecraft experiments, laser ranging, and relativistic timing. Since Newton's era, each generation's measurements have increasingly confirmed Einstein's predictions, constraining alternative theories and revealing subtle nuances. These tests affirm the core principles of general relativity, yet ongoing efforts seek deviations that might illuminate new physics. The pursuit continues, driven by curiosity that anomalies or new phenomena could deepen our understanding of the universe's most fundamental force. The history of gravity testing spans centuries, constantly challenging us to grasp the universe more profoundly and pushing the boundaries of knowledge. When testing gravity in its most extreme and distant environments, we reach a frontier where physics, astronomy, and philosophy intersect. Historically, scientists relied on terrestrial experiments and solar system observations, tracking Mercury's orbit, observing light bending by the Sun, or detecting gravitational waves with LIGO. The universe offers a vast cosmic laboratory, distant objects that challenge our understanding of gravity beyond Earth-based experiments. One of the earliest fundamental tests was the 1919's solar eclipse observation, where Sir Arthur Eddington confirmed Einstein's prediction that light bends passing near the Sun. This supported general relativity, but but involved a relatively weak gravitational field. As telescopes probed deeper into space, more extreme tests emerged involving objects with intense gravity, such as neutron stars and black holes. Neutron stars, especially pulsars, are precise astrophysical clocks. These dense remnants of supernovae spin rapidly, emitting beams that sweep past Earth with exceptional regularity. Binary systems containing pulsars orbiting other neutron stars or white dwarfs serve as natural laboratories. Pulsar timing provides highly sensitive measures of gravitational effects. The Hulse-Taylor binary pulsar, for example, offered the first indirect evidence of gravitational waves. Over years, astronomers observed its orbit shrinking precisely according to Einstein's predictions, confirming the energy carried away by gravitational waves. Black hole candidates also contribute significantly. Matter spiraling into black holes heats up, emitting X-rays that create luminous accretion disks. The behavior of matter in these disks, especially orbital velocities, offers clues about spacetime near the event horizon. Observations with radio telescopes and the Event Horizon Telescope have imaged black hole shadows, confirming Einstein's predictions about the warping of spacetime under extreme gravity. Beyond these compact objects, the large-scale structure of the universe provides crucial tests of gravity. Galaxy clusters, massive systems of hundreds or thousands of galaxies, pose puzzles. The velocities of galaxies within clusters are too high given the visible matter, suggesting the presence of unseen mass, dark matter, or possibly modified gravity theories. The Bullet cluster exemplifies this phenomenon. When two galaxy clusters collide, the hot gas lags behind the galaxies due to collisions, while gravitational lensing maps show most mass aligns with the galaxies, indicating unseen matter. This observation strongly supports dark matter, but has also been used to test alternative gravity theories like modified Newtonian dynamics, MIND, and TVs, which predict different lensing profiles and galaxy rotation behaviors. Large surveys such as the Sloan Digital Sky Survey map galaxy distributions over billions of light years. Analyzing how galaxies cluster and how light from background objects is magnified or bent, gravitational lensing allows scientists to probe gravity across vast distances. The pattern of structure formation and its evolution depend on the laws of gravity and dark energy, with any deviations from Einstein's predictions indicating potential modifications to gravity on cosmic scales. Supernovae, particularly Type Ia, have been instrumental in understanding cosmic gravity. These explosions serve as standard candles due to their consistent brightness. Measuring their apparent brightness and redshift enables astronomers to trace the universe's expansion rate over time. In the late 1990s, supernova observations revealed the universe's expansion is accelerating, implying a repulsive component called dark energy. This discovery links directly to the nature of gravity at large distances. If gravity behaves differently over cosmic scales, supernova brightness redshift relationships would differ from standard models. Gravitational wave astronomy has opened new avenues for testing gravity. The detection of space-time ripples from merging black holes and neutron stars directly confirms Einstein's equations. The properties of these waves, speed, polarization, dispersion, offer stringent tests. For instance, the 2017 neutron star merger, observed both in gravitational waves and electromagnetic signals, confirmed that gravitational waves travel at the speed of light within tight limits. Any deviations, such as altered propagation speed or unexpected polarization, could suggest alternative theories of gravity. The cosmic microwave background, CMB, relic radiation from the early universe, encodes details about gravity's role in structure formation. Fluctuations in temperature and polarization reveal how primordial density perturbations grew under gravity's influence, shaping the cosmos. Precise measurements from satellites like Planck align with the lambda CDM model, but they also constrain alternative gravity theories. All these tests form an interconnected framework, relentlessly probing Einstein's legacy. They challenge us to refine our models or develop new theories to explain the universe's intricate behavior across vast distances and timescales. While gravity has been well validated within the solar system, these cosmic tests suggest it might be part of a larger, more complex picture, possibly an emergent phenomenon or linked to some deeper physics. In this grand cosmic investigation, distant objects are our most revealing informants. They compel us to question whether gravity is a fundamental force as Einstein proposed, or an emergent effect of more profound processes. As we gather more precise data, from pulsars, galaxies, black hole shadows to gravitational waves, the universe continues testing our understanding. The mystery of gravity deepens, inviting us to look beyond conventional notions toward new physics. Scientists explore gravity at small scales through laboratory experiments, aiming to understand whether it behaves differently at tiny distances. While we often think of gravity from stars and galaxies, researchers test its nature directly on Earth, probing distances less than a millimeter or even smaller. This work is akin to listening for a faint whisper of a cosmic secret, but within a controlled lab environment. A fundamental question behind these experiments is whether gravity, which follows the inverse square law at large scales, deviates at short distances. Newton's law states that gravitational force diminishes with the square of distance, and Einstein's general relativity provides a more comprehensive description. However, some theories suggest deviations could occur at very small scales, possibly revealing new physics. To investigate this, scientists perform high-precision measurements using tiny test masses, sometimes weighing just micrograms, placed near controlled source masses. The goal is to detect signals that confirm or challenge the inverse square law. If deviations exist, they might manifest as unexpected forces or anomalies in gravitational attraction. One key device is the torsion pendulum, where a small mass is suspended from a delicate fibre. When another mass is brought nearby, gravitational attraction causes the pendulum to twist slightly. By measuring this torsion precisely, researchers can detect faint gravitational signals and identify deviations from Newtonian predictions. Precision is crucial because electromagnetic forces, atomic interactions, or environmental disturbances can overshadow gravity's subtle effects. Experiments are conducted inside vacuum chambers to eliminate air currents, and they're shielded from electromagnetic interference through Faraday cages and other measures. These precautions ensure the measurements reflect pure gravitational interactions. Another technique is the microcantilever method, in which a tiny, flexible beam bends minutely due to gravitational attraction from a nearby mass. Laser interferometry detects deflections down to fractions of a nanometer. This method offers high sensitivity at very short distances, making it especially useful for probing gravity's behavior at sub-millimeter ranges. Some experiments employ atom interferometry, which uses the wave-like nature of ultra-cold atoms. When cooled near absolute zero, atoms behave coherently, and their wave functions split and recombine. Differences in interference patterns caused by gravitational effects allow scientists to measure tiny potential differences. Atom interferometry can detect anomalies or deviations that point to new physics, including extra dimensions or modified gravity theories. Research also includes patterned structures, arrays of tiny masses arranged precisely at varying densities, to amplify or detect subtle gravitational effects over specific distances. These mass arrays function like gravitational antennas, designed to pick up faint signals or test the universality of gravity at small scales. Despite technological advancements, probing gravity at tiny scales remains challenging because it is the weakest of fundamental forces. Electromagnetic forces often dominate, requiring meticulous precautions, neutralizing surface charges, choosing minimal interaction materials, and maintaining vibration-free, thermally stable environments. Experiments are often conducted deep underground or in isolated facilities to reduce noise from seismic activity, cosmic rays, and environmental disturbances. Recent experiments also seek evidence of fifth forces, hypothetical additional forces beyond the four known fundamental interactions. These forces, extremely weak, could be hidden at small scales and have significant implications if detected. Scientists look for modulations or anomalies in signals at specific distances, or deviations from the expected force law to identify such forces. Some theories propose gravity isn't fundamental but emergent from more basic interactions. If so, experiments at small scales might reveal discrepancies hinting at a deeper underlying structure of the universe. Discovering such deviations would revolutionize physics, potentially unlocking new insights into the nature of reality and dark matter. Pushing the boundaries further, scientists are testing the inverse square law at ever smaller distances, from micrometers to nanometers, using advanced technology. So far, results support the law's validity, setting strict limits on the strength and range of possible new forces or particles. Still, research continues actively, each new experiment tightening constraints and refining models. Laboratory experiments complement astronomical observations, while space-based tests explore gravity across cosmic scales. Terrestrial measurements scrutinize its behavior at the smallest distances. Together, they form a comprehensive approach, testing gravity's fabric from the universe to the lab. Ultimately, probing gravity at small scales challenges assumptions, advances measurement techniques, and delves into the unknown. Despite centuries of study, gravity remains mysterious in some aspects, holding on to secrets that experiments strive to uncover. These efforts are key to understanding whether Newton's and Einstein's descriptions are complete, or if surprises await, hidden clues that could trigger a new revolution in physics. Advances in technology continually extend experimental sensitivity, allowing tests at increasingly smaller scales. For example, experiments have probed down to micrometer and nanometer distances, seeking signals of new physics. So far, outcomes uphold the inverse square law, placing stringent limits on hypothetical forces or particles. Nonetheless, each experiment refines our models, poses new questions, and keeps the quest lively. Such meticulous terrestrial research links closely with broader scientific efforts, enriching our understanding of fundamental forces. These experiments serve as vital complements to cosmic observations. Together, they probe the universe's underlying structure, from the vastness of space to the tiniest laboratory scale. Probing gravity at small scales also involves testing whether it might be an emergent phenomenon rather than a fundamental force, as some speculative theories suggest. If gravity emerges from more fundamental interactions, experiments might reveal deviations, offering profound insights into the universe's underlying principles. Detecting such discrepancies could profoundly alter our understanding, possibly illuminating dark matter or dark energy. In sum, exploring gravity on tiny scales pushes the limits of technology and imagination. It is a meticulous, challenging enterprise, driven by the hope of uncovering surprises that could reshape physics. Despite centuries of study, gravity's secrets still inspire scientists to innovate and experiment, seeking clues that may unlock a deeper comprehension of the universe's fundamental workings. When we look out into the universe, we find a cosmos full of surprises, places where our classical understanding of gravity, formulated by Isaac Newton and refined by Albert Einstein, begins to show cracks. These aren't minor quirks or measurement errors. They challenge the very foundations of physics and hint at deeper, more mysterious layers of reality. Take the outskirts of galaxies. Astronomers observe that stars far from the core move faster than predicted by visible matter alone. According to Newtonian physics, stars should slow down at large distances from the galaxy's center, like planets in our solar system. Instead, their velocities remain constant or even increase. This is the galaxy rotation curve problem, signaling that there's more to the story. This discrepancy led to the hypothesis of dark matter, a mysterious invisible substance permeating galaxies and clusters. Dark matter appears to provide the extra gravitational pull needed to keep those stars in orbit at high speeds. Yet despite extensive searches, dark matter particles remain undetected, evading direct interaction with matter. We're trying to understand invisible scaffolding that guides cosmic motions but resists direct observation. Beyond individual galaxies, these deviations appear in clusters of galaxies, the universe's largest gravitational structures. Gravitational lensing, where light from distant objects bends around massive clusters, often yields effects too strong to be explained solely by visible matter. Again, unseen mass seems to influence light and matter, amplifying gravity beyond our expectations. In the early universe, deviations are even more profound. Cosmological simulations based on ordinary matter and Einstein's gravity produce structures that don't match observations. The universe's large-scale web appears to form more rapidly and extensively than these models predict. To reconcile theories with data, scientists invoke dark matter and dark energy, which influence gravity in ways beyond traditional expectations. Some researchers propose gravity behaves differently under certain conditions. This has inspired modified gravity theories. Instead of adding unseen matter, these approaches suggest tweaking Einstein's general relativity to change how gravity operates at large distances or low accelerations. One notable example is modified Newtonian dynamics, MOND. Instead of dark matter, MOND proposes that Newton's laws need adjustments at extremely weak accelerations, like those at galaxy outskirts. In this model, gravity becomes stronger than expected when forces are small, allowing stars to sustain high velocities without extra mass. For some galaxies, MOND fits observed rotation curves without dark matter, raising the possibility that gravity's laws may not be universal. Another approach involves FR gravity, where Einstein's equations are extended with additional functions of curvature. These models introduce new fields or modifications that influence the universe's expansion and structure formation. While primarily aimed at explaining dark energy's effects, they also predict deviations in gravity under certain conditions, such as within galaxy clusters or during the early cosmos. Observations continue to test these theories. Precise measurements of gravitational lensing and galaxy dynamics help determine whether deviations stem from unseen matter or altered physics. Data sometimes favor dark matter, especially considering cosmic microwave background radiation and the universe's large-scale mass distribution. Yet some findings suggest modified gravity models can explain certain galactic phenomena without unseen matter, though they often struggle to reconcile all observations universally. Beyond galaxies, environments like black holes might reveal deviations hinting at new physics. Near event horizons, phenomena challenge models of spacetime and gravity. Matter spiraling inward and gravitational wave signals offer insights, but discrepancies could hide in these extreme realms. Gravitational waves, ripples in spacetime from black hole or neutron star mergers, are a key probe. So far, detections by LIGO and Virgo match Einstein's predictions closely, confirming general relativity even in intense gravity conditions. As sensitivity improves and more systems are observed, subtle deviations might appear, prompting questions about Einstein's theory and its completeness. The early universe also provides clues. The cosmic microwave background, CMB, observed by missions like Planck, shows faint fluctuations reflecting gravity's behavior shortly after the Big Bang. Deviations from the standard cosmological model could point to alternative gravity theories or unknown particles and forces influencing expansion dynamics. A central challenge remains: how to distinguish effects caused by unseen matter from those arising from fundamental modifications to gravity. This task is complex, similar to discerning whether a faint whisper comes from an invisible source or a different acoustic environment. It demands precise measurements, clever experiments, and scientific ingenuity. What makes these deviations so fascinating is that they hint at a universe more complex than previously thought. They push us to question assumptions, develop new theories, and explore phenomena that might someday revolutionize our understanding of space, time, and fundamental forces. Currently, deviations tend to be subtle and sometimes ambiguous, but they keep scientific frontiers active. Every new observation can possibly overturn decades of physics or guide us toward a unifying theory that explains the cosmos's forces. Perhaps someday, we'll uncover a principle unifying these anomalies and revealing a universe even more wondrous. Until then, the universe remains a vast laboratory, challenging our understanding of gravity. It urges us to probe deeper, think broader, and stay curious. The truth about gravity might be hidden in these deviations, waiting to be uncovered. This puzzle is already reshaping our view of reality and promises to captivate future generations. In essence, these anomalies suggest gravity may not be as simple as it appears. Whether caused by unseen matter or fundamental changes in gravity itself, they remain central to our quest to understand the universe. Ongoing research aims to resolve these questions, and new discoveries could transform our understanding of cosmology and physics alike. Future research in gravity holds great promise as we stand on the brink of new discoveries. Our understanding of this fundamental mysterious force remains incomplete. Upcoming experiments aim to deepen knowledge and could reshape our view of the universe. Next-generation gravitational wave observatories, such as the Einstein Telescope in Europe and Cosmic Explorer in the US, will be more sensitive than current detectors like LIGO. They will probe deeper into space, capturing signals from black hole and neutron star mergers, even from the universe's earliest epochs. These observations test Einstein's general relativity, checking if gravitational waves behave exactly as predicted or if subtle anomalies suggest modifications at high energies or large scales. Space-based observatories, like the Laser Interferometer Space Antenna, LISA, launching in the next decade, will detect gravitational waves from supermassive black hole mergers and early universe phenomena. Free from Earth's seismic noise, LISA can explore mysteries still hidden. Deviations from expected waveforms may hint at alternative gravity theories, including extra dimensions, scalar fields, or modifications at cosmic distances. Pulsar timing arrays, such as North American Nanohertz Observatory, monitor stable pulsars as cosmic clocks. Tiny variations in pulse arrival times over decades could signal low-frequency gravitational waves from supermassive black hole binaries or relics from the early universe. Unexpected discrepancies might reveal that gravity behaves differently on large scales, or that unknown fields influence space-time. Laboratory experiments will also be vital. Future ultra-sensitive torsion balances, atom interferometers, and quantum sensors aim to test gravity at small scales. Some theories propose gravity either weakens or strengthens at sub-millimeter distances, detectable via experiments with bosonic condensates or cold atom systems. These tests could uncover hidden forces or new particles mediating gravity, explaining its apparent weakness compared to other fundamental forces. Space missions dedicated to precise gravitational measurements within our solar system, like Bepi-Colombo to Mercury and lunar orbiters, will test Einstein's predictions with unprecedented accuracy. Tiny deviations might signal new physics, such as extra dimensions or scalar fields affecting gravity near Earth or other celestial bodies. Cosmological observations will clarify gravity's role on the larger scales. Projects like the Rubin Observatory's Legacy Survey of Space and Time will map billions of galaxies, revealing how gravity influences the cosmic web, galaxy clustering, and gravitational lensing. These data could determine whether dark energy is a cosmological constant or a sign of modified gravity. If cosmic acceleration arises from altered gravity, surveys may reveal telltale signs. Studying the early universe's imprints through the Cosmic Microwave Background, CMB, offers promising insights. Missions like the Simons Observatory and CMB-S4 will measure tiny temperature and polarization fluctuations, which may encode signals of gravity during the universe's infancy. Patterns here could suggest high-energy physics behaves differently during cosmic inflation or support alternative gravity theories. Quantum experiments involving superpositions and entanglement seek to connect gravity and quantum mechanics. Researchers aim to determine if gravity can induce quantum effects, or if it behaves differently under quantum conditions. Demonstrating a breakdown of classical gravity at quantum scales might lead to new theories, progressing toward a quantum theory of gravity, or revealing deeper aspects of reality. Tabletop experiments with superconducting circuits or optomechanical systems are promising. Creating macroscopic superpositions and observing gravitational effects can test if gravity is fundamentally classical or quantum. Any deviations from predictions could herald a paradigm shift and aid in developing a unified physics framework. These efforts, ground and space-based observatories, laboratory tests, cosmological surveys, and quantum experiments, collectively expand our understanding of gravity. Each contributes to a growing knowledge base, guiding us from confirming existing theories to discovering surprises that challenge our understanding. This interplay of theory and observation fuels progress, prompting re-examination of space-time's nature. As instruments improve, the universe will continue to surprise us. Increased observational precision is likely to reveal phenomena beyond our current understanding. Rather than discouraging us, this drives curiosity and the relentless pursuit of gravity's fundamental truths. Perhaps our Einsteinian model will evolve into something entirely new, unveiling a deeper principle underlying gravity in the universe. The horizon of future research is filled with potential breakthroughs. Each new experiment brings us closer to understanding whether gravity is a fundamental force woven into reality or an emergent phenomenon from quantum effects. Dark energy and dark matter, mysterious components of the cosmos, may be explained by new gravitational physics or might lead to entirely different frameworks. Every discovery raises questions, maintaining a vibrant pursuit of understanding. Cross-disciplinary collaboration across physics, astronomy, cosmology, and quantum mechanics is essential. Advances in one field often inspire breakthroughs in others, revealing unexpected connections and fostering innovation. Carefully designed experiments will illuminate the shadows where our current understanding falters, potentially leading to a more elegant, comprehensive picture where gravity is seamlessly integrated into the fabric of reality. Increased observational precision will continue to challenge existing theories and inspire new ones. As more data are gathered, understanding deepens, and surprises motivate us to question underlying assumptions. The future holds potential for astonishing insights, and possibly a radical redefinition of gravity itself. The pursuit of understanding gravity is a collective, ongoing effort driven by curiosity and ingenuity. Every experiment, whether observing cosmic phenomena or probing quantum effects, contributes crucial pieces to the puzzle. Over time, these efforts aim to determine if gravity is fundamental, an emergent quantum phenomenon, or part of a greater, undiscovered physics framework. Ultimately, these investigations could explain profound mysteries: dark energy, dark matter, or the unification of gravity with quantum mechanics. Each breakthrough will generate new questions, fueling further exploration. The journey continues, ever evolving and propelled by human curiosity. In this quest, each new insight advances our grasp of reality. As tools improve and observations become more precise, the universe will keep surprising us, fueling imagination and challenging theories. Understanding gravity remains among humanity's most profound scientific pursuits, with the promise of unveiling the fundamental principles of existence itself. Future gravity research is vibrant and evolving, promising to reshape our understanding of the universe. Key directions include quantum gravity, extreme conditions, testing Einstein's general relativity, dark matter and dark energy, modified gravity theories, laboratory experiments, technological tests, astrophysical simulations, and gravitational lensing. The hunt for quantum gravity remains a primary focus. While quantum mechanics and general relativity are foundational, they do not reconcile seamlessly. A universe where gravity exhibits quantum behavior, fluctuations, entanglements, or discrete states could unify physics. Approaches like string theory, proposing fundamental particles as vibrating strings, and loop quantum gravity, suggesting space-time is granular with tiny loops, are leading contenders. Experiments aim to detect subtle quantum effects in gravity, such as influences on quantum states or signatures in cosmic microwave background radiation. Probing gravity under extreme conditions like black holes and neutron stars offers insights into high-energy gravity. Recent detections of gravitational waves from colliding black holes and neutron stars have opened new observational windows. Future detectors like space-based LISA will capture signals from more exotic mergers, possibly revealing deviations from Einstein's predictions and exposing physics beyond current models, especially near singularities or event horizons. Testing Einstein's general relativity in strong fields remains central. Techniques like pulsar timing arrays monitor rotating neutron stars as cosmic clocks, searching for irregularities caused by passing gravitational influences or modifications in space-time. Examining star orbits near supermassive black holes offers further tests. Are Einstein's equations complete, or do surprises await? On cosmological scales, efforts focus on understanding dark matter and dark energy, the universe's dominant components, constituting about 95% of its mass energy. Dark matter influences galaxy rotation, gravitational lensing, and large-scale structure. Uncovering its nature, exotic particles, modified gravity, or other phenomena is a monumental goal. Projects like the Large Synoptic Survey Telescope and space missions seek to differentiate dark matter models and modify gravity theories. Persistent questions include whether gravity weakens or strengthens at cosmic scales, and whether dark energy results from new gravitational behavior. Modified gravity theories propose changes to Einstein's equations at large scales, potentially explaining the universe's accelerated expansion without dark energy. These models suggest gravity may evolve over cosmic distances or timescales. Developing consistent models with local tests and cosmic observations remains challenging. Upcoming surveys will test these theories through galaxy clustering, cosmic microwave background measurements, and gravitational lensing, helping distinguish them from standard cosmology. Laboratory experiments continue to push boundaries. Tiny deviations from Newtonian gravity at sub-millimeter scales are explored with torsion balances and atomic interferometers, aiming to detect hidden extra dimensions or new forces. Some theories suggest gravity weakens at small scales due to extra dimensions, a hypothesis future experiments might confirm or refute. Advances in space-based experiments hold great potential. Proposed satellite missions could test the equivalence principle with extreme precision, measure gravitational constants, and detect anomalies indicating new physics. These experiments aim to probe gravity's universality, search for violations, and refine fundamental understanding. Astrophysical and cosmological simulations are crucial. High-performance computing models cosmic evolution under different gravity scenarios, generating predictions for comparison with observations. Incorporating modified gravity theories into simulations of galaxy formation and large-scale structure will clarify whether Einstein's framework is complete or if new physics are needed, deepening cosmic understanding. Gravitational lensing, like bending around massive objects, serves as a powerful observational tool. Precise lensing measurements map dark matter distribution, test gravity's behavior over vast distances, and evaluate if gravity's strength varies over cosmic timescales. Analyzing these patterns enhances our grasp of the universe's structure and gravity's role in shaping it. The road ahead in gravity research is both thrilling and challenging. Each measurement and theoretical insight peels back layers of the universe's grand design, whether uniting quantum mechanics with gravity, deciphering dark components, or discovering new forces. These efforts deepen our grasp of this fundamental force and challenge worldview assumptions. Advances in experiments, observations, and simulations continually push boundaries, promising breakthroughs. Yet mysteries remain. Gravity's true nature, the fabric of space-time, dark matter and energy's roles, and potential new physics all await discovery. The pursuit of quantum gravity may lead to a unified theory uniting the quantum realm with space-time. Examining gravity near black holes could reveal deviations from established theories, hinting at deeper laws. Understanding dark matter's identity and dark energy's nature might revolutionize cosmology and physics. Modified gravity models offer alternatives for cosmic acceleration, tested through large-scale surveys. Laboratory experiments continue probing tiny deviations, searching for hidden extra dimensions or forces. Technological advances, especially in space-based experiments, promise unprecedented sensitivity. Proposed missions could test the equivalence principle with extraordinary precision, measure gravitational constants, and detect subtle anomalies. These efforts aim to probe gravity's universality, search for violations, and refine fundamental insights. Simulations provide a testing ground for theories, helping shape future observations and experiments. Gravitational lensing continues revealing the universe's large-scale structure, offering clues about gravity's behavior on cosmological scales. The interplay between theory and observation fuels the ongoing quest, as discoveries raise new questions and possibilities. The future of gravity research is a fascinating frontier, an evolving landscape where each step uncovers deeper cosmic truths, revealing the universe's profound mysteries. Understanding gravity's nature promises scientific breakthroughs and reshapes our fundamental conception of reality, highlighting the universe's complexity and wonder. At this frontier, researchers remain eager to explore the secrets gravity still holds, recognizing that the universe's story remains far from complete. Imagine a universe where the tiniest particles and largest cosmic structures are interconnected by rules so intricate that our current theories barely grasp them. The quest for a theory of quantum gravity seeks to unify the incompatible worlds of quantum mechanics and general relativity. When we talk of gravity in Einstein's framework, we describe a smooth space-time fabric that bends and warps in response to mass and energy. But at the smallest scales, where quantum effects dominate, this smoothness dissolves into a froth of probabilities and uncertainties. A quantum gravity theory aims to bridge this divide, providing a seamless understanding of gravity at scales smaller than an atom. This effort could dramatically reshape our understanding of the universe's fabric. Currently, Einstein depicted space-time as a smooth, four-dimensional manifold that curves with matter and energy. Quantum mechanics, however, hints that space-time might be fundamentally discrete, made of tiny units that give rise to the smooth fabric we observe on larger scales. Instead of a continuous expanse, space-time could emerge from fundamental entities such as loops, strings, or other quantum constructs. This shift would mean moving from a classical field description to a picture where space-time arises from underlying quantum foundations. String theory offers one promising framework. It proposes that the universe's basic units are tiny vibrating strings, with different vibrations producing particles and forces, including gravity, via a mode called the graviton. If validated, string theory could answer long-standing questions about singularities, those infinite densities inside black holes or at the Big Bang, where our current physics fails. Instead of infinite values, a quantum gravity approach based on strings might smooth these out into finite, comprehensible entities that would transform our understanding of the universe's origins and black hole interiors. Another compelling approach is loop quantum gravity, which suggests that space itself is composed of tiny loops woven into a quantum net. At the Planck scale, the realm of the infinitesimal, space-time might be granular, consisting of discrete chunks rather than a continuous medium. This could mean gravity emerges from interactions among these loops. If true, it might reveal that gravitational attraction is a manifestation of quantum interactions at minuscule scales. This idea would fundamentally shift our view, transforming gravity from a geometric property into something rooted in quantum entanglements and states. Implications extend far beyond theorem and models. They could revolutionize how we understand cosmic birth, evolution, and fate. Quantum gravity could clarify the moments immediately after the Big Bang, replacing the concept of a singular explosive point with a quantum bounce, a phase where quantum effects prevented infinite densities, suggesting a cyclic universe oscillating through phases of contraction and expansion. Such models might explain why the universe is so finely tuned and shed light on dark energy and its role in accelerated expansion, reshaping cosmic narratives. Black holes, inherently mysterious, would also be understood differently. Classical physics views their cores as points of infinite density, a singularity beyond the reach of our laws. Quantum gravitational insights might eliminate these singularities, revealing finite cores or subtle quantum hair, imprints storing information previously thought lost forever. This development could resolve the black hole information paradox, merging quantum mechanics with gravity and offering clues about spacetime's quantum structure. On a practical level, a unified quantum gravity theory could deepen our understanding of phenomena at energy scales unreachable today, such as cosmic ray collisions or conditions inside black holes. While recreating these energies on Earth is impossible now, the theory could predict observable phenomena, detectable in signals like gravitational waves or subtle deviations from Einstein's predictions. Advanced detectors could pick up signatures of quantum effects from the early universe, providing indirect evidence of the quantum nature of gravity. A complete quantum gravity framework could also clarify dark matter and dark energy, mysterious components that comprise most of the universe's mass energy. Perhaps these phenomena are manifestations of quantum effects on cosmic scales or remnants of the universe's quantum structure. Understanding their true nature could revolutionize cosmology, suggesting that what we perceive as unseen matter or energy might directly result from the quantum architecture of spacetime. Long-term, a quantum understanding of gravity could spark new technologies. Just as quantum mechanics revolutionized computing, encryption, and sensing, understanding quantum spacetime could lead to breakthroughs. Quantum sensors might one day detect minute effects of quantum gravity, and new physics could emerge from harnessing the quantum properties of spacetime itself, opening innovative fields and applications we can't yet imagine. What excites scientists most is that grasping quantum gravity could answer fundamental questions about the universe's origin, why it exists, why constants have their specific values, and what lies beyond observable horizons. It's a search for the most profound understanding of reality, revealing the universe's true nature on the most fundamental level. The journey toward this understanding involves significant challenges, especially since directly testing quantum gravity is daunting. Energies involved are far beyond current experimental capabilities. Nonetheless, scientists pursue indirect evidence, examining the cosmic microwave background for quantum imprints, observing gravitational waves from the universe's earliest moments, or detecting tiny deviations from Einstein's predictions. Each discovery brings us closer to a complete picture. Ultimately, a successful theory of quantum gravity would do much more than unify two physics pillars. It would reshape our cosmic worldview. It would show that spacetime, gravitation, and quantum phenomena are threads woven into a single interconnected fabric, an awe-inspiring tapestry revealing a universe woven from the quantum fabric of reality itself. This frontier beckons us, promising to transform our understanding from the smallest particles to the vast cosmic web. To deepen our understanding of gravity, significant technological advancements are needed across multiple scientific and engineering domains. Currently, gravity remains one of the least understood fundamental forces, especially at quantum scales and in its influence on dark matter, dark energy, and space-time itself. Exploring gravity further requires tools capable of probing the universe with unprecedented precision across a broad spectrum, from quantum particles to galaxy clusters, often under extreme conditions. The following are key technological developments necessary to push the boundaries of our knowledge. Space-based observatories are essential as Earth-based telescopes face atmospheric interference. To measure tiny space-time distortions caused by gravitational waves or local mass distributions, we need ultra-sensitive space telescopes with adaptive optics and laser interferometry. Missions like the European Space Agency's Laser Interferometer, Space Antenna, LISA, exemplify this, aiming to detect gravitational waves from colossal events such as supermassive black hole mergers or early universe phenomena. LISA's success depends on advancing laser interferometry techniques that measure minute distance changes, on the order of picometers, over millions of kilometers with extreme precision. Improving laser stability, mirror reflectivity, and noise reduction in space-based interferometers is crucial. Developing next-generation space gravitational wave detectors could open new observational windows, enabling detection of sources beyond current horizons and testing gravity under conditions impossible to replicate on Earth. Microscopic scale experiments require innovative laboratory tools employing quantum measurement techniques. Ultra-cold atoms, quantum sensors like atom interferometers, and optomechanical systems can detect subtle deviations from Einstein's predictions at sub-millimeter or even micrometer scales. Enhancing the sensitivity, coherence times, and stability of these systems will help determine if gravity behaves differently when quantum effects dominate. Such experiments may reveal modifications predicted by quantum gravity theories or hidden interactions like fifth forces, offering clues about unifying gravity with other fundamental forces. Terrestrial gravimetric and accelerometric technologies also demand revolutionary improvements. Highly sensitive superconducting gravimeters and advanced atomic interferometry-based gravimeters can measure gravity variations with sub-milligauss accuracy, where 1 gal equals 1 centiAstrosex2. Improving their stability, noise immunity and calibration could enable detection of minuscule gravitational anomalies associated with underground structures, geological processes, or unknown mass-energy distributions. These devices might uncover new physics, such as gravity propagation anomalies or interactions with dark matter fields, by monitoring real-time gravity variations across environments. Satellite technology must advance for better mapping of Earth's gravity with higher resolution and accuracy. Missions like GRACE have demonstrated satellite gravimetry's power in understanding planetary mass redistribution. Future missions with more precise gyroscopes, laser ranging systems, and accelerometers could detect tiny deviations from Newtonian predictions, tracking gravity changes over time and space at millimeter-level precision. These improvements are vital for identifying anomalies that may signal new physics or modifications to general relativity, aiding our understanding of gravity's role in cosmic evolution and structure formation. High-energy particle accelerators are another frontier. Although primarily for particle physics, larger and more powerful accelerators could investigate whether gravity interacts differently at high energies. Such experiments could explore quantum gravity phenomena, search for hypothetical particles like gravitons, or test theories such as supersymmetry and extra dimensions. Upgrading existing colliders or building new ones with enhanced detection capabilities could uncover interactions or particles providing insight into gravity's quantum nature. Quantum technologies, including quantum entanglement, quantum computing, and quantum communication, offer promising avenues for detecting minute effects of gravity at quantum scales. Entanglement-based sensors could test the interplay between quantum mechanics and gravitational fields, probing the quantum structure of space-time, developing stable, long-distance quantum networks, and maintaining entanglement over extended periods are essential steps. These sensors could reveal deviations from classical gravity, illuminate the quantum properties of space-time, and enable quantum simulations of gravitational phenomena, leading to breakthroughs in understanding gravity at small scales. Computational advancements are critical for modeling extreme gravitational environments such as near black holes or during the early universe. High-performance supercomputers combined with machine learning and AI, can simulate complex gravitational systems, interpret observational data, and predict novel phenomena. Developing algorithms to solve Einstein's field equations in complex scenarios or incorporate quantum effects is essential for guiding experiments and understanding observations, especially when dealing with nonlinear interactions in strongly curved space-time. Data analysis and signal processing. Techniques must evolve to handle vast gravitational data volumes and extract faint signals amid noise. Advanced algorithms employing pattern recognition, neural networks, and real-time filtering are necessary to identify gravitational wave signals, anomalies, or deviations from theoretical predictions. Improving sensitivity enhances detection of unexpected phenomena, hinting at new physics. As gravitational wave astronomy matures, combining multi-messenger data, electromagnetic signals, neutrinos, and gravitational waves requires sophisticated tools for integration and analysis. Interdisciplinary collaboration across physics, engineering, computer science, materials science, and astronomy is vital. Cross-disciplinary exchange accelerates development of innovative detection methods, robust materials, and advanced data analysis techniques. Establishing international research programs, open data repositories, and collaborative platforms fosters rapid progress by sharing insights, refining experiments, and coordinating efforts toward breakthroughs in gravitational physics. Finally, fostering a culture of curiosity, innovation, and investment is essential. Breakthroughs often come from unexpected places, so sustained funding for fundamental research, experimental facilities, and technological development is crucial. Educating future scientists in interdisciplinary approaches ensures continuous progress. Public engagement and outreach can inspire broader support, fueling further investment in these ambitious endeavors. In sum, understanding gravity's true nature requires groundbreaking advances across observational, experimental, computational, and theoretical domains. Precision space missions, quantum sensors, high-energy accelerators, advanced computational techniques, and collaborative efforts will gradually unravel the mysteries of gravity, potentially revealing physics beyond current theories. These technological innovations will open new windows into cosmic workings, perhaps ultimately revealing the quantum fabric of spacetime and resolving fundamental questions about the universe's structure and origin. Unlocking gravity's secrets demands relentless innovation, cross-disciplinary synergy, and unwavering curiosity. Only then can humanity fully comprehend this elusive force. The question of whether gravity can be harnessed or manipulated through technology ventures into one of science's greatest frontiers. For centuries, gravity was an inscrutable force, an invisible tug holding planets in orbit, keeping us grounded and shaping the universe. As our understanding of this fundamental force has grown, so have dreams of controlling or utilizing it for human benefit. Could we develop technologies that manipulate gravity itself? Could we harness it as an energy source, propel spacecraft without rockets, or engineer gravity to create new environments? These tantalizing and seemingly impossible possibilities push us to explore the boundaries between what is conceivable and what is achievable. Understanding what gravity really is helps in pondering whether it can be harnessed. According to Einstein's general relativity, gravity isn't just a force pulling objects together, it's the curvature of spacetime caused by mass and energy. Massive objects distort the fabric of spacetime, guiding the motion of other objects and creating the perception of gravitational attraction. Unlike electromagnetic forces, which can be amplified or cancelled using fields and materials, gravity is fundamentally tied to the universe's geometry. Its weakness compared to electromagnetic forces makes manipulation especially challenging. Gravity is approximately 600 trillion times weaker than electromagnetic forces at the scale of a proton. Despite these challenges, scientists have hypothesized intriguing ideas for influencing gravity or mimicking its effects artificially. One persistent concept involves gravitational shielding, hoping that specific materials or configurations might reduce or block gravitational influence locally. If feasible, developing such shielding could revolutionize transportation and infrastructure. Yet currently, there's no experimental evidence supporting gravitational shielding. Our current understanding suggests attempts to create such effects conflict with established principles of general relativity and conservation laws. Another approach involves creating artificial gravity through acceleration or rotating frames, what's called centrifugal gravity. This is already used in spacecraft like the International Space Station by spinning habitats to generate a force that mimics gravity. Though not true manipulation of gravity, it leverages motion to engineer gravitational effects. Future technology might generate larger, more controlled artificial gravity environments via advanced rotation or acceleration mechanisms, facilitating long-term space colonization. Still, this relies on inertial effects of acceleration, not direct control over the gravitational field. High-energy physics also offers speculative avenues. Some theories consider gravity as an emergent phenomenon arising from quantum interactions. If that's true, manipulating the underlying quantum states could influence gravitational effects, perhaps enabling gravity shielding or localized modifications. Such ideas open the possibility of creating gravity wells on demand or controlling the strength of gravity regionally. But these remain speculative. We're still lacking a complete, experimentally confirmed theory of quantum gravity. String theory and loop quantum gravity are highly abstract, and practical methods for gravitational manipulation remain far off. Advances in materials, science, and astrophysics may someday yield insights. Discovering exotic states of matter, like superfluids or Bose-Einstein condensates, could reveal unusual gravitational interactions. Some models propose quantum states might subtly influence local spacetime curvature. However, experimental evidence is lacking, and any effects are expected to be minimal at best. Revolutionary ideas include harnessing gravity through hypothetical devices called gravity generators or gravitonic machines, potentially producing controlled gravitational effects by emitting or manipulating particles called gravitons. If gravitons exist, as some quantum gravity theories suggest, future technology might produce focused streams of these particles to generate localized gravitational fields or counteract gravity temporarily. Yet, this remains speculative. Detecting and controlling gravitons are among physics' most profound challenges. In broader terms, concepts like space-time engineering or gravitational technology feature prominently in science fiction. Devices that can propel ships faster than light, create artificial gravity, or make planets more hospitable. While exciting,